The search for life beyond Earth takes us far from the familiar, into the depths of the cosmos, where alien worlds beckon with the promise of possibility. Among countless planets orbiting distant stars, some stand out, worlds with conditions that could sustain life as we know it, or perhaps life as we've never imagined. Join us as we journey to these extraordinary exoplanets, exploring their mysteries, marveling at their potential, and uncovering what makes them the most likely candidates for habitability in the universe. The answers to humanity's greatest questions might just lie on their distant horizons. Exploring the universe, the unseen worlds of exoplanets. In the vastness of the universe, stars twinkle like tiny lanterns, illuminating the potential for other worlds far beyond our own. These unseen companions of distant stars, called exoplanets, have captured the imagination of scientists and dreamers alike. Exoplanets, planets orbiting stars other than our Sun, offer tantalizing glimpses of places that might harbor life or redefine what we know about planetary systems. Since their discovery, exoplanets have become the heart of one of the most exciting frontiers of modern astronomy. The story of exoplanets is a tale of persistence, innovation, and the relentless curiosity that drives humanity to peer beyond the veil of the familiar. Let's explore the key discoveries and techniques that have brought these distant worlds into focus. The first confirmed detection of exoplanets wasn't what anyone expected. In 1992, astronomers Alexander Vulshan and Dale Frail discovered two planets orbiting a pulsar, a rapidly spinning neutron star known as PSRB 1257+12. These pulsar planets, forged in the aftermath of a supernova explosion, are among the most hostile environments imaginable. Yet their discovery proved that planets could exist in places once deemed impossible. Interestingly, these worlds weren't found orbiting a Sun-like star, as many theorists had anticipated. Instead, the discovery forced scientists to reconsider their assumptions about where planets could form and thrive. The hunt for exoplanets took off from there, with astronomers refining their techniques to uncover worlds in more hospitable regions of the galaxy. If you were to point your telescope at the night sky, what are the odds of finding a planet like Earth? Surprisingly slim, yet also incredibly promising. Estimates suggest that only about 1 in 10,000 stars may host an Earth-like planet. However, with hundreds of billions of stars in the Milky Way, this still leaves millions of potential candidates. The discovery of super-Earths and mini-Neptunes has further expanded the spectrum of planetary possibilities, revealing that our solar system is but one blueprint among countless variations. Finding exoplanets is a bit like detecting a moth fluttering near a distant street lamp. The challenges are immense, yet astronomers have developed ingenious methods to overcome them. The transit method, for instance, detects the tiny dip in starlight that occurs when a planet passes in front of its star. This technique has been instrumental in identifying planets as small as Earth, including some within their star's habitable zone. Meanwhile, the radial velocity method, which measures the subtle wobble of a star caused by the gravitational pull of an orbiting planet, has unveiled planets invisible to transit studies. This method is especially adept at detecting massive gas giants, often referred to as hot Jupiters, which orbit perilously close to their stars. These discoveries challenged early assumptions about planetary formation, leading to new models that explain how such giant planets could migrate inward after forming farther from their stars. A lesser-known but equally fascinating technique is astrometry, which involves tracking the precise motion of a star over time to detect the gravitational influence of orbiting planets. Though underutilized, this method holds promise for detecting Earth-like planets in the future. The discovery of hot Jupiters, gas giants with blistering temperatures due to their proximity to their stars, upended traditional theories of planetary formation. Scientists initially believed that gas giants like Jupiter could only form in the cold outer reaches of a star system. Yet hot Jupiters, such as 51 Pegasi b, were found orbiting much closer to their stars than Mercury is to the Sun. These planets, with their swollen atmospheres and scorching surfaces, forced a re-evaluation of planetary migration and system dynamics. Planets are born from swirling disks of gas and dust that surround young stars, known as protoplanetary disks. These glowing disks emit infrared radiation, which astronomers use to study the early stages of planet formation. The intricate dance of particles within these disks eventually leads to the creation of planetesimals, the building blocks of planets. By observing these disks, scientists have gained insights into how planetary systems, including our own, take shape. The study of exoplanet atmospheres is where the search for life begins. When a planet transits its star, some of the starlight passes through its atmosphere, allowing astronomers to analyze its composition. This technique has already revealed water vapor, methane, and even carbon dioxide on distant exoplanets. The discovery of hazes and clouds has added complexity to the study, as these features can obscure or alter the atmospheric signals. For example, the presence of sodium and potassium absorption lines in an atmosphere indicates a hot, gaseous environment, while molecules like methane might hint at the potential for biological activity. The ability to detect these faint signatures is a testament to the precision of modern astronomy. Many exoplanets orbit so close to their stars that they are tidally locked, meaning one side always faces the star while the other remains in perpetual darkness. While this might seem inhospitable, regions known as terminator zones, the boundary between the day and night sides, could provide temperate conditions suitable for life. These unique environments highlight the diversity of habitable conditions that might exist beyond Earth. Some exoplanets exhibit retrograde orbits, meaning they revolve around their stars in the opposite direction of the star's rotation. This bizarre phenomenon challenges existing models of planetary formation, which suggest that planets should form an orbit in the same direction as their stars spin. Retrograde orbits are likely the result of gravitational interactions or catastrophic collisions during a system's chaotic youth. A significant number of exoplanets exist in binary star systems, where two stars orbit each other while hosting their own planetary companions. These circumbinary planets often experience complex gravitational forces, leading to highly dynamic and sometimes unpredictable orbits. Planets in such systems can enjoy prolonged periods of illumination from both stars, creating unique conditions for potential habitability. Unlike the evocative names of mythological deities that grace the planets in our solar system, exoplanets are often assigned catalogue numbers. While practical for scientific purposes, these designations, like Kepler 452b or TOI 700DD, lack the romantic allure of names like Mars or Venus. However, public initiatives such as the IAU Name ExoWorlds campaign allow people worldwide to suggest names, adding a human touch to these distant worlds. The star a planet orbits plays a crucial role in its habitability. Stellar activity, such as flares and radiation bursts, can strip atmospheres from planets or bathe them in harmful ultraviolet light. At the same time, a star's magnetic field and long-term stability are critical for maintaining habitable conditions. The interplay between a planet and its star is a delicate balance, with profound implications for the evolution of planetary environments. The discovery of exoplanets has revealed a cosmos far stranger and more diverse than we ever imagined. From fiery hot Jupiters and rogue wanderers to Earth-like candidates and ocean worlds, the universe is teeming with possibilities. Each discovery brings us closer to answering one of humanity's oldest questions. Are we alone? Unlocking the blueprint for life. What makes a planet habitable? When searching the cosmos for life, we're not just looking for any planet, we're searching for the extraordinary conditions that allow life to flourish. Earth serves as our singular template, but habitability is far more nuanced than simply finding a world with liquid water. The universe, vast and varied, may hold surprises beyond our current understanding. In this section, we will explore the less obvious, often overlooked factors that determine a planet's potential for habitability. Beyond the basic Goldilocks zone, we'll uncover the intricate web of planetary and stellar characteristics that must align to support life as we know it, or even life as we don't. The presence of liquid water is considered the gold standard for habitability. However, the conditions required for water to exist in a liquid state are more complex than they appear. Planets with high atmospheric pressure can keep water liquid at greater temperature extremes, expanding the range of environments where it might be found. Tidal forces from nearby moons or stellar companions can create internal heat, melting subsurface ice into liquid water, as seen on icy moons like Europa and Enceladus, which are considered potential habitats for life. Conversely, worlds with slow rotations might concentrate water in permanent polar ice caps, limiting its availability for sustaining life. That said, life may not always depend on water. The concept of alternate solvents, like methane or ammonia, expands the possibilities for exotic biochemistry. Planets in close orbits around their stars often become tidally locked, with one side perpetually facing the star while the other remains in eternal darkness. For decades, tidal locking was seen as a death sentence for habitability. However, new models suggest that the terminator zone, the twilight strip between day and night, could host temperate conditions where life might thrive. Atmospheric circulation on tidally locked planets may redistribute heat, creating regions of relative stability. Even the dark side might harbor life if geothermal heat prevents complete freezing. The metallicity of a star, its abundance of elements heavier than hydrogen and helium, directly impacts planetary formation. Stars with higher metallicity are more likely to host rocky planets, as these elements form the building blocks of terrestrial worlds. Interestingly, the Milky Way's metallicity gradient means inner regions of the galaxy are more likely to host Earth-like planets. Metal-poor stars, while rarer, could create systems with fewer gas giants, reducing gravitational disruptions for terrestrial planets. This link between stellar chemistry and planetary potential underscores the interconnectedness of cosmic processes. A planet's magnetic field serves as its first line of defense against stellar radiation. Without it, solar winds can strip away atmospheres, as happened to Mars. Magnetic fields arise from a planet's molten metallic core, but not all cores are created equal. Larger planets may sustain magnetic fields longer due to slower core cooling. Additionally, magnetic interactions with a parent star or moon can sustain dynamo activity, as seen with Jupiter's moon, Ganymede. Habitability isn't just about atmosphere. It's about protecting that atmosphere from relentless cosmic forces. On Earth, the carbon silicate cycle regulates global temperatures over geological timescales. Similar cycles could stabilize climates on exoplanets. Volcanism releases carbon dioxide, warming the atmosphere, while weathering removes CO2, cooling the planet. Without such feedback loops, planets risk entering runaway scenarios, freezing like Mars or overheating like Venus. The presence of plate tectonics, a hallmark of geochemical cycling, is thus a critical, though difficult to detect, factor in planetary habitability. Size matters when it comes to planetary habitability. A planet that is too small, like Mars, may lose its atmosphere over time. Conversely, a planet that is too large, like Neptune, may retain a thick envelope of hydrogen and helium, making surface conditions uninhabitable. Super-Earths, planets larger than Earth but smaller than Neptune, are of particular interest. Their stronger gravity can sustain thick atmospheres and active geologies, potentially supporting life for billions of years. While we often think of oceans as a life-sustaining feature, their geophysical role is equally crucial. Oceans act as heat redistributors, moving warmth from equators to poles, preventing extreme temperature gradients that might destabilize climates. Moreover, oceans regulate atmospheric composition by absorbing CO2 and other gases. Subsurface oceans, insulated by ice, might support life in environments shielded from harsh surface conditions. Even planets lacking surface oceans could host liquid water beneath kilometers of ice. A planet's albedo, or the fraction of sunlight it reflects, plays a critical role in its climate. High albedo planets, such as those covered in ice or clouds, reflect most of their star's energy, potentially plunging them into global freeze. Conversely, low albedo worlds absorb more heat, which might push them into a runaway greenhouse state. Interestingly, planets with variable albedo, driven by seasonal changes or cloud cover, could experience dynamic climates that foster biodiversity. The habitable zone traditionally refers to the region around a star where liquid water can exist. However, the concept of the abiogenesis zone broadens this perspective. This zone considers not just liquid water, but also the presence of energy gradients and complex chemistry, key ingredients for the origin of life. Planets with geothermal activity, subsurface oceans, or unique atmospheric compositions might support life even outside traditional habitable zones. The type and thickness of an atmosphere determine whether a planet can support life. Thicker atmospheres retain heat, creating a buffer against stellar variability. High oxygen levels might be a biosignature, but excessive amounts could be toxic to some life forms. Meanwhile, planets with high levels of hydrogen and methane could host life forms unlike anything on Earth. The interplay between pressure, temperature, and chemistry creates a wide spectrum of potential environments. A star's lifespan directly influences its planet's habitability. Short-lived stars like massive O-type stars burn out in a few million years, too brief for complex life to develop. In contrast, red dwarfs, with lifespans of trillions of years, offer long-term stability, but pose challenges due to intense stellar flares. Sun-like stars strike a balance, providing billions of years of steady luminosity. The age of a star also affects its planetary system. Older stars may lose their protoplanetary disks, limiting planet formation, but also reducing disruptive debris impacts. Planets with eccentric orbits face extreme seasonal changes as they swing closer to and farther from their stars. While this might seem inhospitable, eccentricity could drive climate diversity, potentially fostering robust ecosystems in dynamic environments. Seasonal melting and freezing might create temporary lakes or rivers. Life forms could adapt to cyclical extremes, thriving during optimal conditions. These worlds challenge the idea that stability is the only path to habitability. As scientists refine their understanding of habitability, it becomes clear that life could thrive under conditions far removed from those on Earth. From tidally locked planets to subsurface oceans and super-Earths, the criteria for habitability are as diverse as the planets themselves. Our search for life is a journey not just across space, but into the nature of existence itself. Closer than we think, the most habitable exoplanets nearby. The search for life beyond Earth often conjures images of galaxies far, far away. Yet some of the most intriguing candidates for habitability lie much closer, cosmically speaking. Within a few dozen light-years, astronomers have identified exoplanets that might host life, offer insights into planetary evolution, or even become future destinations for humanity. Orbiting the red dwarf Proxima Centauri, just 4.2 light-years away, Proxima Centauri b is the closest known exoplanet to Earth. Discovered in 2016, this rocky world lies within its star's habitable zone, where conditions might allow liquid water to exist. Its mass, about 1.2 times that of Earth, suggests it could have a rocky surface, making it a prime candidate for studies on Earth-like planets. However, Proxima Centauri's frequent stellar flares pose a challenge for its atmosphere, potentially stripping it over time. Despite these risks, Proxima b's orbital period of just 11 days offers a unique environment for studying tidally locked worlds. Recent studies hint at the possibility of an atmosphere retained by magnetic fields, though direct evidence is pending. Proxima Centauri b's nearness makes it a prime candidate for missions like Breakthrough Starshot, which aims to send nanospacecraft to the star system within a few decades. At 40 light-years away, LHS 1140b orbits a small, quiet red dwarf star in the constellation Cetus. What makes this planet extraordinary is its density and potential habitability. LHS 1140b is about 1.6 times the size of Earth, but over 6 times as massive, suggesting a rocky composition with a dense core. The planet resides in the habitable zone and receives less radiation than Proxima b, which increases its chances of retaining an atmosphere. If present, this thick atmosphere might harbor water vapor or other life-supporting elements. Due to its slow star and stable environment, LHS 1140b has been dubbed a best-case scenario for habitability among super-Earths. Its relative closeness and favorable conditions make it a frequent target for atmospheric studies using telescopes like the James Webb Space Telescope, JWST. In 2017, astronomers announced the discovery of a planetary system with 7 Earth-sized planets orbiting the ultra-cool dwarf star, TRAPPIST-1, located just 39 light-years away. 3 of these planets, TRAPPIST-1e, TRAPPIST-1f, and TRAPPIST-1g, lie in the star's habitable zone. TRAPPIST-1e is the most Earth-like, with a density and composition suggesting a rocky surface. TRAPPIST-1f might have an ocean-covered surface, making it a candidate for water world status. TRAPPIST-1g, while larger and colder, could support subsurface oceans. The system's planets are tidally locked, yet their proximity to one another allows for fascinating possibilities, such as interplanetary migration for hypothetical life forms. If an advanced species evolved in this system, hopping between planets might be as simple as crossing continents on Earth. Located 11 light-years away, Ross 128b orbits a red dwarf star that is significantly less active than Proxima Centauri, offering an advantage for habitability. Ross 128b receives similar levels of radiation to Earth, making its surface conditions potentially mild. The planet's close orbit, with a 9.9-day year, places it firmly in the star's habitable zone. The reduced stellar activity increases the likelihood that the planet has retained its atmosphere. As one of the calmest nearby planets, Ross 128b has become a key target for studying how habitability can exist around red dwarfs. Orbiting the red dwarf, Gliese 1061, just 12 light-years away, Gliese 1061 days, is a less well-known but equally fascinating candidate. It resides at the outer edge of the habitable zone, where surface temperatures could allow for liquid water under the right conditions. Its mass, at about 1.75 times that of Earth, suggests it is likely rocky. Despite being less studied, its proximity makes it a prime target for future telescopic surveys. This world serves as a reminder that even lesser-known exoplanets can offer profound opportunities for discovery. The second closest star to Earth, Barnard's Star, hosts a planet called Barnard's Star B, about 6 light-years away. The planet is a super-Earth, with a mass over 3 times that of Earth. Its orbit places it in a cold zone, but its potential geothermal activity might sustain subsurface liquid water. As one of the oldest stars known, Barnard's Star and its planet offer a glimpse into the early universe's planetary systems. While not a classical habitable zone candidate, Barnard's Star B challenges our assumptions about where life could exist. At 12 light-years away, Tau Ceti is one of the nearest Sun-like stars. Among its planets, Tau Ceti F stands out. It lies at the outer edge of the habitable zone, where a thick atmosphere could prevent freezing temperatures. The system's low metallicity offers a different perspective on planetary formation, as its planets formed in an environment with fewer heavy elements. Tau Ceti's planets are among the closest analogues to our own solar system, despite their subtle differences. Discovered in 2019, Teegarden's Star C orbits its host star just 12 light-years away and boasts an Earth-similar temperature range. Teegarden's Star C is part of a 2-planet system, both of which lie near the habitable zone. Its star is ancient, providing a stable environment over billions of years. This planet is notable for its Earth-similar habitability index, ESI score, making it one of the most promising candidates for further study. Located 14 light-years away, Wolf 1061c occupies the inner edge of its star's habitable zone. It is a super-Earth with a mass over 4 times that of Earth. The planet's proximity to its star suggests extreme temperature gradients, with the potential for habitable conditions on specific regions of its surface. Wolf 1061c represents a dynamic environment where habitability could depend heavily on atmospheric circulation. At 13 light-years away, Captain B orbits one of the oldest stars known, Captain Star. The planet is over 11 billion years old, making it more than twice as old as Earth. Its age suggests that it may have had ample time for life to develop, evolve, or even vanish. Captain B offers a unique opportunity to study how habitability might evolve over cosmic timescales. The proximity of these exoplanets makes them prime targets for current and future telescopes, such as the James Webb Space Telescope, and ground-based observatories like the Extremely Large Telescope, ELT. By studying these nearby worlds, astronomers hope to uncover not only the conditions necessary for life, but also the diversity of planetary systems in the universe. These planets, though close in astronomical terms, remain tantalizingly out of reach for now. However, with advancing technology, humanity may one day visit or even settle these alien worlds. Until then, they remain a beacon of hope, a reminder that the universe may hold other homes just waiting to be found. The Breath of Worlds, decoding exoplanet atmospheres. A planet's atmosphere is more than just a veil of gas. It's the key to its character, climate, and potential for life. From fiery infernos to icy shrouds, exoplanet atmospheres are as diverse as the worlds they envelop. Studying these alien skies has become a cornerstone of modern astronomy, revealing secrets about planetary evolution, weather, and even hints of habitability. When light from a distant star passes through a planet's atmosphere, some of it is absorbed, leaving telltale fingerprints in the star's spectrum. This method, known as transmission spectroscopy, allows scientists to identify the molecules present in an exoplanet's atmosphere. Each molecule absorbs light at specific wavelengths, creating a unique signature that astronomers can decode. Using this technique, researchers have detected a variety of atmospheric elements on distant worlds, including water vapor, carbon dioxide, methane, and even exotic chemicals like titanium oxide. One of the most detailed atmospheric analyses comes from WASP-39b, a hot Jupiter located about 700 light-years away. Thanks to the James Webb Space Telescope, JWST, scientists discovered high levels of sulfur dioxide, a molecule typically produced by photochemical reactions driven by the star's intense light. Traces of water vapor, sodium, and potassium were also found, painting a picture of a dynamic, volatile atmosphere. WASP-39b's atmosphere offers a glimpse into the complex chemistry of gas giants and how stellar radiation shapes their skies. On some gas giants, helium dominates the atmosphere, creating conditions vastly different from anything in our solar system. For instance, GJ 3470b, a Neptune-like exoplanet, shows evidence of atmospheric helium escaping into space, forming a vast tail that glows faintly in ultraviolet light. Helium atmospheres may form on planets that lose their hydrogen envelopes due to intense stellar radiation, leaving behind a lighter, more buoyant gas. These findings challenge our understanding of planetary evolution and highlight the role of stellar activity in shaping atmospheres. The weather on exoplanets often defies earthly logic. HD 189733b, a hot Jupiter located 64 light-years away, experiences winds exceeding 10,000 kilometers per hour, faster than the rotation of its host star. The same planet likely has glass rain, as silicate particles condense in its atmosphere, creating storms that would shred anything caught in their path. These extreme weather systems provide insights into atmospheric dynamics on worlds far removed from the conditions we know. Some exoplanets are veiled in haze layers that obscure their true nature. Planets like GJ 1214b, a potential water world, have thick hazes that make it difficult to study their lower atmospheres. Hazy atmospheres often contain hydrocarbons or sulfur compounds, which can scatter light, and create colorful, reflective skies. These atmospheric layers act as both a challenge and a clue, hinting at the underlying chemistry of these worlds. On some exoplanets, temperatures increase with altitude, creating a phenomenon known as a temperature inversion. This is often caused by molecules like titanium oxide or vanadium oxide, which absorb stellar radiation efficiently. Atmospheric dynamics that redistribute heat can also form layers with distinct thermal properties. Understanding these inversions helps scientists build detailed models of how heat and light interact in alien atmospheres. Water is a cornerstone of life as we know it, and detecting water vapor on exoplanets is a significant milestone. Some notable discoveries include K2-18b, a super-Earth in the habitable zone of its star, where water vapor was detected in the atmosphere, raising hopes for habitability. HAT P11b, a Neptune-like planet, also shows clear evidence of water vapor, demonstrating that such compounds can exist even on gas giants. The presence of water vapor doesn't guarantee habitability, but it provides a crucial clue in the search for potentially life-supporting environments. Nitrogen, a major component of Earth's atmosphere, is surprisingly rare in the exoplanetary data collected so far. This scarcity could be due to the challenges of detecting nitrogen spectroscopically, as its spectral lines are weaker than those of other molecules. Variations in planetary formation processes might also favor other elements in certain environments. Finding a nitrogen-rich atmosphere on an exoplanet would be a groundbreaking discovery, potentially signaling Earth-like conditions. Some exoplanets resemble Venus, with runaway greenhouse effects that trap heat and create hostile conditions. Thick carbon dioxide atmospheres on certain hot exoplanets amplify surface temperatures to extreme levels. High albedo due to reflective clouds might temporarily mitigate runaway heating, but can't halt the process entirely. These worlds offer cautionary tales about the delicate balance required to maintain habitability. Super-Earths, planets larger than Earth but smaller than Neptune, often have unique atmospheric compositions. Some super-Earths might retain thick, hydrogen-rich atmospheres that could support high-altitude lifeforms. Others could develop secondary atmospheres, dominated by volcanic outgassing or impacts. The diversity of super-Earth atmospheres highlights the adaptability of planets to their environments. While exomoons have yet to be definitively detected, their potential atmospheres are a subject of intense speculation. A moon orbiting a gas giant in a star's habitable zone could capture gases from its parent planet, forming a hybrid atmosphere. Tidal heating might sustain active geology and volcanism, creating conditions that could support life. The atmospheres of exomoons might offer unique combinations of elements rarely seen on planets. Detecting biosignature gases, compounds that indicate biological activity, is the holy grail of atmospheric studies. Potential biosignatures include oxygen and ozone, which can result from photosynthetic processes, and methane, often produced by life forms, though it can also arise from geological activity. Phosphine has recently been suggested as a potential biosignature after its detection in Venus's atmosphere sparked debates. Finding these gases in the right combinations could provide the first concrete evidence of life beyond Earth. Using advanced instruments, scientists have begun creating thermal emission maps of exoplanets, revealing their temperature distributions. These maps show hotspots that correspond to areas receiving direct starlight and cooler regions caused by atmospheric circulation or shadowed zones. These temperature maps help build a complete picture of an exoplanet's climate and weather systems. Spectroscopic studies of exoplanet atmospheres are poised for a revolution with next-generation telescopes like the Extremely Large Telescope, ELT, and Habitable Worlds Observatory. These instruments will detect fainter signals, allowing for the study of smaller Earth-sized planets. They will also identify trace molecules with unprecedented precision, including potential biosignatures, and explore the atmospheres of rogue planets and exomoons, expanding the scope of habitability research. Exoplanet atmospheres are the bridges between worlds, revealing secrets about their composition, evolution, and potential for life. From the scorching skies of hot Jupiters to the misty hazes of water worlds, each atmosphere tells a story, one that scientists are just beginning to understand. The Moon Factor: how moons could shape exoplanet habitability. When we think about the search for life beyond Earth, our focus often rests on planets. Yet Earth's own history tells a different story. Our moon has profoundly shaped the conditions that sustain life here. From stabilizing the planet's axial tilt to driving tidal cycles, moons have a quiet but powerful influence on habitability. In the search for life in the universe, exomoons, moons orbiting exoplanets, are emerging as potential havens for life. While none have been definitively confirmed yet, their existence is statistically inevitable, and their potential for habitability rivals that of their host planets. Let's delve into the role of moons in creating and sustaining life on distant worlds. Earth's moon plays a critical role in stabilizing the planet's axial tilt, preventing extreme shifts that could lead to wildly fluctuating climates. Similarly, large moons orbiting exoplanets could stabilize their host planet's tilt, creating a predictable and stable climate. This effect would be particularly crucial for planets with eccentric orbits, or those in dynamic systems, such as binary star systems. Without such stabilization, a planet might experience chaotic changes in temperature and seasons, which could hinder the development of life. Moons generate tidal heating through gravitational interactions with their host planets. This phenomenon can produce heat even in frigid environments. Europa and Enceladus, moons of Jupiter and Saturn, have subsurface oceans kept liquid by tidal heating despite their icy surfaces. Exomoons orbiting gas giants in habitable zones could experience similar tidal heating, creating conditions for liquid water beneath an ice shell. This internal heating could sustain subsurface ecosystems, powered by hydrothermal vents, an environment where life on Earth may have first emerged. While much attention is given to planets in the habitable zone, moons orbiting planets within this zone might also enjoy favorable conditions. Exomoons could inherit the protective magnetic field of their host planet, shielding them from stellar radiation. Moons with atmospheres might develop climates conducive to surface liquid water, especially if they retain heat from tidal forces or greenhouse gases. These worlds could become prime candidates for life, combining the advantages of planetary and lunar systems. Moons don't just benefit from their host planets. They can also protect planets from cosmic hazards. Large moons may act as gravitational shields, deflecting asteroids and comets that might otherwise collide with the planet. By absorbing impact events, moons reduce the frequency of catastrophic disruptions, giving life on the planet a chance to evolve uninterrupted. This symbiotic relationship highlights how moons and planets work together to create stable environments. A strong magnetic field is essential for shielding life from harmful stellar radiation, and moons can contribute to this defense. Exomoons with metallic cores might generate their own magnetic fields, adding an extra layer of protection for the planet. The interaction between a moon's and a planet's magnetic fields could create dynamic auroras, offering clues about their magnetic properties. The detection of such interactions could provide indirect evidence of exomoons and their habitability. Moons like Europa and Enceladus are often called ocean worlds because their subsurface oceans are prime candidates for life. Exomoons could similarly harbor vast oceans beneath icy crusts. These oceans might be insulated by thick ice layers, protecting them from surface radiation and temperature extremes. Hydrothermal vents on the ocean floor could sustain ecosystems independent of sunlight, as they do on Earth. The discovery of such moons in the habitable zone would dramatically expand the potential locations for life in the universe. In systems with multiple moons, the interplay between these natural satellites could create unique dynamics. Gravitational interactions between moons might generate additional tidal heating, amplifying their habitability potential. Moons could exchange material through impacts or volcanic activity, spreading organic compounds across the system. Planets with rich lunar systems might host interconnected ecosystems where life evolves in tandem across moons. Exomoons with dense atmospheres could mimic the conditions of small planets. Moons with volcanic activity might release gases that form thick atmospheres, similar to early Earth. Dense atmospheres could trap heat, creating temperate climates even at greater distances from the star. Studying exomoon atmospheres will be a critical step in assessing their potential for habitability. Just as some planets are ejected from their star systems to become rogue planets, moons might also become rogue moons, drifting through interstellar space. Rogue moons with thick atmospheres could retain enough heat to sustain subsurface oceans. These moons might carry the remnants of ecosystems from their original systems, becoming cosmic lifeboats for life. While speculative, the existence of rogue moons would further diversify the range of environments where life might exist. Many exomoons are expected to be tidally locked to their host planets, with one side always facing the planet. This creates unique conditions. The planet-facing side might benefit from reflected light and heat, creating milder conditions than on the far side. Variations between the two hemispheres could drive atmospheric circulation, spreading heat across the moon. Tidal locking adds complexity to the habitability equation, offering both challenges and opportunities for life. Finding exomoons is a significant challenge due to their small size and faint signals. Transit timing variations, TTVs, are one method, as moons can cause slight delays or advances in a planet's transit across its star. Direct imaging of moons is currently beyond our reach, but might become possible with next-generation telescopes. Despite these hurdles, the indirect detection of exomoons is a promising avenue for future discoveries. In rare cases, moons might orbit each other while collectively orbiting a planet, forming a double moon system. The tidal forces between these moons could generate heat, boosting habitability. Double moons might share resources, exchanging water or organic compounds through impacts or geological processes. These unique configurations add another layer of complexity to lunar systems. While much of the focus on exomoons revolves around microbial life, they could also support advanced ecosystems. Moons with Earth-like gravity and atmospheres might host forests, oceans, and diverse fauna. The interaction between moons and their planets could create dynamic environments that foster evolution. In science fiction and science alike, exomoons remain some of the most intriguing possibilities for advanced life. Their unique characteristics, ranging from tidal heating and subsurface oceans to protective atmospheres, make them prime candidates for habitability. The evolution of exoplanets, shaping worlds across eons. Planets are not static. They evolve over billions of years, shaped by the forces of their formation, interactions with their stars, and cosmic events. Exoplanets, distant worlds beyond our solar system, are no exception. Their evolution is a complex and ongoing saga, a process that determines whether they become fiery infernos, icy wastelands, or potential cradles for life. One of the most surprising discoveries about exoplanets is their tendency to migrate. Unlike the orderly arrangement of our solar system, many exoplanets shift dramatically from their original positions. Hot Jupiters, massive gas giants that orbit perilously close to their stars, likely formed much farther away. Their migration inward is driven by gravitational interactions with the protoplanetary disk or neighboring planets, disrupting planetary systems by ejecting smaller planets or altering their orbits. Some planets may migrate outward, forming eccentric orbits that challenge traditional models of system stability. Planetary migration underscores the chaotic and dynamic nature of planetary systems. A planet's atmosphere is both its shield and its vulnerability. Over time, stellar radiation and cosmic events can strip atmospheres away. Planets close to their stars, like those orbiting red dwarfs, are particularly vulnerable to atmospheric erosion caused by stellar winds and flares. Smaller planets with weak gravity, such as Mars analogues, are less able to retain their atmospheres, making them prone to desiccation. Hydrogen and helium, the lightest elements, are often the first to escape, leaving behind secondary atmospheres formed through volcanic outgassing or impacts. The loss or retention of an atmosphere can determine a planet's habitability, highlighting the delicate balance required for life-supporting conditions. Planets in close orbits around their stars often become tidally locked, with one side perpetually facing the star while the other remains in eternal darkness. Tidally locked planets experience extreme temperature differences, with scorching day sides and frozen night sides. However, simulations suggest that atmospheric circulation could redistribute heat, creating habitable conditions in the terminator zone, the boundary between day and night. While tidal locking was once thought to be a barrier to habitability, it may instead create unique environments where life could thrive. Collisions between planetary bodies play a pivotal role in shaping planets. The giant impact hypothesis suggests that Earth's moon was formed by a collision between the young Earth and a Mars-sized body named Theia. Such impacts can strip away atmospheres, alter planetary rotations, and redistribute surface materials, as seen on Uranus, whose tilted axis may result from a massive collision. On exoplanets, giant impacts might trigger volcanic activity, reset atmospheric compositions, or even seed the planet with water and organic compounds. These violent events are not just destructive, they can also be catalysts for planetary evolution. The concept of a runaway greenhouse effect is a stark reminder of how planetary evolution can go awry. Venus serves as a cautionary tale, with its thick carbon dioxide atmosphere trapping heat and creating surface temperatures hot enough to melt lead. Similar processes could occur on exoplanets that begin with Earth-like conditions, but lose their water to space or develop thick, heat-trapping atmospheres. Runaway greenhouse effects highlight the fine line between habitability and uninhabitability. A planet's evolution is deeply intertwined with the activity of its host star. Young stars are often highly active, emitting intense ultraviolet and X-ray radiation that can strip atmospheres and alter surface chemistry. Over time, stars like our Sun enter a more stable phase, providing consistent energy that allows planets to develop complex ecosystems. Dying stars can transform their planetary systems, as seen in white dwarf systems, where planets are exposed to intense radiation and gravitational forces. Understanding stellar activity is crucial to predicting the long-term evolution of exoplanets. The metallicity of a star, its abundance of elements heavier than hydrogen and helium, plays a significant role in the formation and evolution of its planets. High metallicity stars are more likely to host rocky planets, as metals are essential for building planetary cores. Low metallicity systems may form fewer gas giants, reducing the likelihood of disruptive migrations that can destabilize smaller planets. Metallicity offers a glimpse into the chemical diversity of planetary systems and their evolutionary pathways. A planet's core dynamics influence its geological activity and ability to generate a magnetic field. Magnetic fields protect atmospheres from stellar winds and cosmic radiation, as seen on Earth. Over time, a planet's core may cool and solidify, weakening its magnetic field and exposing it to atmospheric loss. Planets with active cores, such as super-Earths, may retain magnetic fields for billions of years, extending their habitable lifespans. The presence of plate tectonics is a key factor in maintaining a stable climate. Tectonic activity drives the carbon silicate cycle, a natural thermostat that regulates atmospheric carbon dioxide levels over geological timescales. Planets without tectonics, like Venus, may lack this self-regulating mechanism, leading to runaway greenhouse conditions. Detecting signs of tectonic activity on exoplanets would provide valuable insights into their long-term habitability. Planets with eccentric orbits experience significant variations in distance from their stars, leading to extreme seasonal changes. These variations can create dynamic climates, with periods of intense heating followed by prolonged cooling. While challenging for life, such conditions could drive evolutionary adaptations, similar to how extreme environments on Earth have produced unique ecosystems. Eccentric orbits add complexity to the study of exoplanetary climates, offering both challenges and opportunities for habitability. Water worlds, planets covered entirely by oceans, offer a unique perspective on planetary evolution. Deep oceans may inhibit plate tectonics, reducing the recycling of nutrients essential for life. Over time, water worlds might lose their oceans to space if exposed to intense stellar radiation or impacts. Despite these challenges, water worlds remain intriguing candidates for hosting life, particularly in subsurface environments. The gravitational interactions between planets in a system can profoundly affect their evolution. Resonances between planets can stabilize their orbits, creating predictable conditions over billions of years. Conversely, close encounters with gas giants or other massive planets can eject smaller planets from the system or alter their orbits. These interactions highlight the interconnected nature of planetary systems and their collective impact on habitability. As stars age, their habitable zones shift outward, exposing previously frozen planets to warming temperatures. Planets that were once too cold might enter the habitable zone, as seen in models of white dwarf systems. However, the increased radiation from aging stars may also strip atmospheres, creating a narrow window of habitability. This evolutionary process adds a temporal dimension to the search for life. The materials that form planets are forged in the hearts of stars and redistributed through supernovae. Supernovae enrich the interstellar medium with heavy elements, providing the building blocks for rocky planets. Planets forming in regions of recent stellar death may have unique compositions, with higher concentrations of certain elements. This cosmic recycling links planetary evolution to the life cycle of stars, creating a deep connection between planets and the universe. The evolution of exoplanets is a testament to the dynamic and interconnected nature of the universe, from their formation in swirling disks of gas and dust to their transformations under the influence of gravity, radiation, and collisions. Planets are constantly changing. These changes determine their potential to host life and their role in the cosmic tapestry. By studying the evolution of exoplanets, we gain not only a deeper understanding of these distant worlds, but also a clearer picture of our own planet's past and future. Water worlds, oceans beyond imagination. When envisioning habitable worlds, it's easy to think of Earth, a planet defined by its oceans, which cover 71% of its surface and regulate its climate. But the universe holds the potential for worlds that are even more dominated by water, where oceans stretch across entire planets, reaching depths far beyond those on Earth. These water worlds or ocean planets challenge our understanding of habitability, offering unique environments that could support life. Water worlds are planets with vast global oceans covering their entire surface. Unlike Earth, where continents rise above the seas, these planets lack exposed land masses. Their oceans can be hundreds of kilometers deep, dwarfing Earth's average ocean depth of 3.7 kilometers. Beneath these oceans, high pressures create layers of exotic ices, such as Ice 7, which is denser than the ice found on Earth. Water worlds likely form in regions of planetary systems rich in water ice, where planets accrete large amounts of volatile compounds during their formation. The birth of a water world begins in the protoplanetary disk, the swirling mass of gas and dust surrounding a young star. In colder regions of the disk, beyond the snowline, water exists as ice, increasing the likelihood of planets forming with abundant water content. If such planets migrate inward, their icy layers melt, creating vast oceans. This migration may explain the presence of water worlds in regions closer to their stars, challenging the notion that only rocky planets can exist in habitable zones. The depth of the oceans on water worlds creates immense pressures at the seabed, leading to the formation of high-pressure ice layers. Ice 7 and Ice X are phases of ice that form under extreme pressures, potentially creating a solid layer beneath the ocean. This ice barrier could separate the ocean from the planet's rocky mantle, limiting the exchange of nutrients and minerals. Despite this, subsurface ecosystems might thrive near hydrothermal vents, where chemical energy provides a foundation for life. The salinity of oceans on water worlds plays a crucial role in their dynamics. High salinity increases the density of water, affecting ocean currents and heat distribution. Salty oceans are also better at retaining heat, which could stabilize the planet's climate. The balance of salinity and temperature might determine whether a water world supports life or becomes a frozen wasteland. Several exoplanets are believed to be potential water worlds based on their densities and locations. Gliese 1214b, located 48 light-years away, is a super-Earth with a thick atmosphere, believed to harbor a deep ocean beneath its clouds. K218b, situated 124 light-years away, shows evidence of water vapor in its atmosphere, indicating the possibility of a liquid ocean. TOI 1452b, a recently discovered exoplanet in a binary system, is thought to be a water world based on its mass and radius, which suggest a composition rich in volatiles. These planets offer tantalizing glimpses into the potential diversity of water worlds. Water worlds might host life not on their surfaces, but in subsurface oceans. On Earth, deep-sea hydrothermal vents teem with life powered by chemical energy rather than sunlight. Similar conditions could exist on water worlds, where geothermal heat from the planet's core provides energy for life. Subsurface ecosystems would be shielded from stellar radiation and meteor impacts, making them stable environments for life to evolve. The atmospheres of water worlds play a critical role in their habitability. A thick water vapor atmosphere can create a strong greenhouse effect, warming the planet even if it is far from its star. However, excessive water vapor can lead to a runaway greenhouse effect, where the planet becomes too hot to support life. Understanding the balance between these atmospheric forces is key to identifying habitable water worlds. While water worlds are often associated with oceans, they can also become global ice houses. If a water world moves too far from its star or loses its atmosphere, its oceans could freeze into a solid crust of ice. Beneath this icy exterior, subsurface oceans might still exist, kept warm by tidal heating or geothermal energy. These frozen water worlds resemble moons like Europa and Enceladus in our own solar system, which are considered prime candidates for extraterrestrial life. On Earth, ocean currents like the Gulf Stream distribute heat across the planet, moderating climates. On water worlds, currents driven by salinity, temperature, and planetary rotation could create stable climates in some regions, while leaving others in extremes. Tidally locked water worlds might develop strong currents that transfer heat from the star-facing side to the dark side, preventing freezing. These dynamic systems could create niches where life might thrive. The cloud albedo effect, the reflection of sunlight by clouds, plays a significant role in the climate of water worlds. Thick clouds can cool the planet by reflecting sunlight, while thin clouds might trap heat and warm the surface. Variations in cloud cover could lead to dramatic climate shifts, creating challenges for habitability. Studying the balance of cloud formation on water worlds is crucial for understanding their long-term stability. Not all water worlds need to be in the habitable zone to support life. Planets with thick atmospheres or strong greenhouse effects might maintain liquid oceans even at great distances from their stars. Rogue water worlds drifting through interstellar space could sustain subsurface oceans insulated by ice and warmed by internal heat. These outliers expand the definition of habitability, challenging the notion that life requires proximity to a star. Identifying water worlds is no easy task. Current techniques rely on a combination of factors. Density measurements indicate water worlds as having densities lower than rocky planets, but higher than gas giants, suggesting a composition rich in water and other volatiles. Atmospheric spectroscopy, which detects water vapor, hydrogen, and oxygen, provides additional clues about the planet's composition. Future telescopes like the James Webb Space Telescope JWST, and the European Extremely Large Telescope, EELT, will enhance our ability to detect and study these fascinating worlds. While the conditions on water worlds differ significantly from Earth, they might still support life. Subsurface oceans offer protection from radiation, creating stable environments for microbial life. Chemical energy from hydrothermal vents could sustain ecosystems in the absence of sunlight. Advanced life, if it exists, would likely evolve differently on water worlds, adapting to the unique challenges of a planet without land. The discovery of life on a water world would redefine our understanding of biology and its resilience. Water worlds are among the most intriguing exoplanets, offering a glimpse into environments vastly different from Earth. Their vast oceans, dynamic atmospheres, and potential for life make them prime candidates for exploration. Exotic exoplanets, worlds stranger than fiction. The universe has always held surprises, but nothing quite captures the imagination like the diversity of exoplanets. From worlds raining molten glass to planets made of diamond, these celestial bodies stretch the limits of what we thought possible. They remind us that the cosmos is not bound by the familiar rules of our solar system. It's a playground of extremes, where the bizarre becomes the norm. Imagine a planet where the surface sparkles like a jewel, a carbon planet, composed largely of diamond and graphite. These exotic worlds form around stars with a high carbon-to-oxygen ratio. Instead of silicate rocks, their crusts are made of carbon compounds, including graphite and diamond. 55 Cancri e, a super-Earth 40 light-years away, is a potential carbon planet. Its dense carbon-rich composition suggests that vast deposits of diamonds may exist beneath its surface. Such planets challenge our understanding of geology and hint at the economic potential of mining resources beyond Earth. Some planets exist so close to their stars that their surfaces are transformed into molten hellscapes. These lava worlds include 55 Cancri e, which orbits its star in just 18 hours, with surface temperatures over 2,000 degrees Celsius, creating rivers and oceans of molten rock. Another example is K2-141b, where supersonic winds whip across the planet, redistributing molten material from the day side to the night side. These worlds are not just extreme, they're dynamic laboratories for understanding volcanic processes on a planetary scale. Among the most mysterious exoplanets are those that absorb nearly all the light that hits them. These dark planets appear as pitch-black voids against the backdrop of space. TRES 2b, located 750 light-years away, reflects less than 1% of the light from its star, making it darker than coal. The planet's darkness is likely caused by its atmosphere, which contains light-absorbing chemicals like titanium oxide and vanadium oxide. Such planets defy our understanding of planetary albedo and challenge atmospheric models. Not all planets are dense and rocky. Some, known as superpuffs, have extremely low densities. Kepler 51c, for instance, has the mass of Neptune, but a density so low it would float in water. These planets are likely surrounded by thick, hydrogen-rich atmospheres that make them appear inflated. Their puzzling compositions challenge models of planetary formation and evolution, suggesting that nature can produce far lighter structures than previously imagined. On some exoplanets, hydrogen has been stripped away by intense stellar radiation, leaving behind helium-dominated atmospheres. GJ 3470b, a Neptune-like planet, shows evidence of helium escaping into space, forming a faint, ghostly trail. Helium planets are rare, but offer insights into atmospheric erosion and the long-term evolution of gas giants. Their ethereal appearance adds to the growing catalogue of planetary diversity. In some alien atmospheres, silicate clouds form, creating rainstorms of molten glass. These phenomena are found on planets like HD 189733b, a hot Jupiter where winds exceed 7,000 kilometers per hour, and rain consists of tiny glass particles that reflect blue light, giving the planet its azure hue. The combination of silicate clouds and extreme winds creates storms unlike anything seen on Earth. These dramatic weather systems reveal how the interplay of heat and chemistry produces truly alien conditions. When gas giants venture too close to their stars, their atmospheres are stripped away, leaving behind their dense rocky cores, Chthonian planets. Torwai 849b is a prime example, with a mass similar to Neptune but no gaseous envelope. These planets offer a rare glimpse into the interior composition of gas giants, revealing the cores that would otherwise remain hidden beneath thick atmospheres. Chthonian planets are a stark reminder of the destructive power of stellar radiation. Most planets orbit in the same plane as their star's equator, but polar orbit planets defy this norm. These planets move perpendicular to their star's rotation, creating unusual seasonal cycles. The formation of such orbits is thought to involve complex gravitational interactions, such as those in multi-star systems. Polar orbit planets challenge traditional models of planetary system dynamics. While many large planets are gas giants, mega-Earths are massive rocky planets. Kepler 10c, one of the first discovered, has 17 times the mass of Earth but remains solid with a dense rocky composition. These planets are thought to form in regions with high metallicity, where heavy elements dominate planetary formation. Mega-Earths blur the line between terrestrial planets and gas giants, offering clues about the upper limits of rocky planet formation. Planets orbiting two stars, known as circumbinary planets, have long fascinated astronomers. Kepler 16b, the first confirmed example, orbits a pair of stars in a system reminiscent of Tatooine from Star Wars. These planets experience complex illumination patterns, with two suns rising and setting at irregular intervals. Circumbinary planets add an extra layer of complexity to the study of planetary climates and habitability. Some exoplanets follow highly eccentric orbits, swinging close to their stars before retreating into deep space. HD 80606b, for example, has an orbit so elliptical that its temperature rises by 1000 degrees Celsius during its closest approach to its star. These planets experience dramatic seasonal changes, offering a natural laboratory for studying extreme climates. Their eccentricity challenges traditional theories of planetary stability and evolution. Some gas giants, known as puffy planets, are much larger than their mass would suggest. WASP-12b is a prime example, with a radius nearly twice that of Jupiter, but only 1/3 of its density. These planets are thought to be inflated by intense heating from their stars, which causes their atmospheres to expand. Their unique properties highlight the complex relationship between a planet and its host star. Some super-Earths are kept warm, not by their stars, but by tidal heating. Gravitational interactions with their host planets or neighboring moons generate internal friction, heating the planet's interior. These planets could sustain volcanic activity and subsurface oceans, even at great distances from their stars. Tidally heated super-Earths offer a new avenue for exploring habitability beyond the traditional habitable zone. The exotic exoplanets we've discovered so far represent just a fraction of what's out there. Each new discovery challenges our assumptions and expands our understanding of what planets can be. From worlds made of diamond to planets adrift in interstellar space, the cosmos continues to surprise and inspire. The search for biosignatures, traces of life in alien worlds. The search for life beyond Earth has long been one of humanity's greatest scientific quests. While exoplanets offer tantalizing hints of other habitable environments, the discovery of biosignatures, chemical or physical evidence of life, would be the definitive breakthrough. These markers could range from gases in a planet's atmosphere to peculiar surface features that can only be explained by biological activity. Biosignatures are signs that life might exist or might have existed on a planet or moon. They can be divided into two main categories. Chemical biosignatures are gases or molecules in an atmosphere, such as oxygen, methane, or phosphine, that could be produced by living organisms. Morphological biosignatures are physical features, such as microbial mats or sedimentary structures, that indicate biological activity. The challenge lies in distinguishing between biological and abiotic processes, as many of these markers can also be produced through non-living chemical reactions. Oxygen is a hallmark of life on Earth, produced primarily through photosynthesis. On an exoplanet, a high concentration of oxygen coupled with ozone could signal biological processes. However, oxygen alone is not definitive, as it can be generated through the photodissociation of water by ultraviolet light. Its coexistence with methane or other reducing gases is a much stronger biosignature, as these gases typically react and destroy each other, requiring continuous replenishment by living organisms. Detecting both oxygen and methane in the atmosphere of an exoplanet would be a major milestone in the search for life. Methane is another promising biosignature, as it is produced by both biological and geological processes. On Earth, methane is released by microbes, especially in anaerobic environments like wetlands or the digestive systems of animals. Geological processes, such as serpentinization, can also produce methane, so its detection alone is not conclusive. The key is to analyze the isotopic composition of methane, which can distinguish between biological and abiotic sources. Unfortunately, current technology is not yet advanced enough to perform this analysis on exoplanets. In 2020, scientists announced the detection of phosphine in the atmosphere of Venus, sparking intense debate. On Earth, phosphine is associated with anaerobic bacteria and industrial processes. The conditions on Venus are extreme, with surface temperatures hot enough to melt lead, making biological explanations for phosphine intriguing but highly speculative. If phosphine is detected on exoplanets, it could serve as a biosignature, but distinguishing it from abiotic sources will require careful analysis. Photosynthetic life on Earth produces a distinct spectral feature known as the red edge. This occurs because plants reflect infrared light, creating a sharp increase in reflectance at certain wavelengths. Detecting a similar red edge on an exoplanet could indicate the presence of vegetation or other photosynthetic organisms. While the red edge is highly specific to Earth-like life, it serves as a template for identifying other biological processes. One of the more subtle biosignatures involves observing seasonal variations in a planet's atmosphere. On Earth, carbon dioxide levels fluctuate with the seasons due to plant growth and decay. Similar patterns on exoplanets could indicate the presence of seasonal life cycles. Seasonal variations provide an additional layer of evidence that complements other biosignatures. In some environments, life may produce gases unfamiliar to us on Earth. For example, dimethyl sulfide, DMS, is produced by marine plankton and could serve as a biosignature in ocean worlds. On Titan-like exoplanets, life might generate methanol or ammonia, exploiting chemical pathways adapted to cold, methane-rich environments. By expanding our understanding of biochemistry, scientists aim to identify biosignatures that reflect a broader diversity of life. Biosignatures can also be detected in the way light interacts with a planet. On Earth, light scattered by biological aerosols such as pollen or microbial clouds produces a distinct polarization pattern. Similarly, oceans can create a glint effect, indicating the presence of liquid water, which could support life. Polarized light provides an indirect but powerful tool for studying potential biosignatures. Life often disrupts its environment, creating a state of chemical disequilibrium. On Earth, the coexistence of oxygen and methane in the atmosphere is a clear example of disequilibrium maintained by biological processes. On exoplanets, identifying similar imbalances could point to active life forms. Disequilibrium studies are particularly useful for distinguishing between biological and abiotic processes. While the search for biosignatures often focuses on atmospheres, subsurface oceans may also harbor life. Moons like Europa and Enceladus in our solar system have shown evidence of water vapor plumes, which could contain organic compounds. Similar phenomena on exoplanets or exomoons could provide direct evidence of life. Subsurface biosignatures may offer an alternative pathway to discovering extraterrestrial ecosystems. Super-Earths, with their strong gravity and thick atmospheres, offer unique environments for detecting biosignature gases. Their larger size makes it easier to observe spectral features from their atmospheres. However, their high pressure and temperature may also lead to false positives, as abiotic processes could mimic biological activity. Careful analysis of super-Earth atmospheres is essential for distinguishing genuine biosignatures. Detecting biosignatures requires advanced technology, and several upcoming missions aim to push the boundaries. The James Webb Space Telescope, JWST, will analyze the atmospheres of nearby exoplanets for chemical markers like water, methane, and carbon dioxide. The planned Habitable Worlds Observatory, HWO, will be specifically designed to detect biosignatures on Earth-like planets. Ground-based telescopes like the Extremely Large Telescope, ELT, will provide high-resolution spectroscopy to study planetary atmospheres in unprecedented detail. These missions promise to transform the search for biosignatures, bringing us closer to finding life beyond Earth. One of the biggest hurdles in the search for biosignatures is avoiding false positives. Abiotic processes, such as volcanic eruptions or photochemical reactions, can produce gases like methane and oxygen. Stellar activity can also alter atmospheric chemistry, creating misleading signals. To overcome these challenges, scientists use contextual analysis, examining multiple factors such as the planet's environment, star type, and orbital characteristics. While most biosignatures focus on microbial or simple life, the search for technosignatures, evidence of advanced civilizations, is gaining traction. Detecting industrial chemicals like CFCs or nitrogen oxides could indicate technological activity. Infrared emissions from large-scale structures, such as Dyson spheres, might reveal the presence of advanced engineering. Though speculative, technosignatures expand the scope of the search for extraterrestrial life. The hunt for biosignatures is a multidisciplinary effort, combining astronomy, biology, chemistry, and planetary science. Each discovery, whether it's a subtle chemical imbalance or a dramatic spectral feature, brings us closer to answering the profound question of whether we are alone in the universe. Terraforming exoplanets, turning alien worlds into new Earths. The concept of terraforming, modifying a planet's environment to make it habitable for human life, has long been a staple of science fiction. Yet, as our knowledge of exoplanets grows, the idea of reshaping alien worlds becomes less fantastical and more a question of engineering and ethics. Terraforming could offer humanity a way to expand beyond Earth, transforming barren or hostile planets into thriving, life-sustaining worlds. But how feasible is terraforming? What technologies would it require? And which exoplanets are the most promising candidates? This section explores the scientific, technological, and ethical dimensions of terraforming exoplanets. Terraforming involves altering a planet's atmosphere, surface, or climate to make it more Earth-like. This could include increasing atmospheric pressure to allow liquid water to exist, adding oxygen to create a breathable atmosphere, modifying temperature to fall within a habitable range, or introducing water to arid worlds through comet impacts or ice mining. The process is theoretically possible, but faces enormous challenges, from the energy required to the timescales involved. Some exoplanets are more suitable for terraforming than others due to their size, location, and existing conditions. Promising candidates include Proxima Centauri b, located just 4.2 light-years away. This rocky planet lies in its star's habitable zone, and if it has a thin atmosphere or liquid water, terraforming efforts could focus on enriching its air with oxygen and stabilizing its climate. Gliese 667 cc, a super-Earth in a multi-star system, is believed to have a rocky surface and stable temperatures, making it an ideal target for terraforming. K218b, with evidence of water vapor in its atmosphere, offers a head start in creating Earth-like conditions, though its thick atmosphere may require significant modification. These planets combine proximity with the potential for existing resources, reducing the technological barriers to terraforming. One of the first steps in terraforming is generating a breathable atmosphere. This could be achieved by seeding the atmosphere with greenhouse gases, such as carbon dioxide, to warm the planet and increase pressure. Releasing oxygen-producing microbes, like genetically engineered cyanobacteria, could convert carbon dioxide into oxygen over time. Introducing nitrogen, which makes up the bulk of Earth's atmosphere, would stabilize the air and reduce flammability. Challenges include avoiding runaway greenhouse effects, or creating an atmosphere too toxic or unstable for human habitation. For exoplanets on the colder edge of their star's habitable zone, raising the temperature is critical. Potential methods include orbiting solar mirrors to concentrate sunlight on specific regions, melting ice and warming the surface. Greenhouse gas injections, such as methane or CO2, could trap heat, creating a warming effect. Redirecting icy comets to crash into the planet would release water vapor and heat, jump-starting the warming process. However, the risk of overcorrection, leading to extreme temperatures or atmospheric instability, must be carefully managed. Water is a cornerstone of habitability, and many exoplanets may lack sufficient surface or atmospheric water. Solutions include mining ice from asteroids or moons and transporting it to the planet to create lakes, rivers, and oceans. Triggering volcanic activity could release trapped water vapor from the planet's mantle. Artificial reservoirs, using advanced materials, could store and distribute water across arid regions. Water delivery would need to be balanced to prevent flooding or destabilizing tectonic activity. While gas giants like Jupiter seem inhospitable, their moons, or even specific layers of their atmospheres, might be suitable for human habitation. Floating cities could be constructed in the dense atmospheres of gas giants, where pressure and temperature are Earth-like at certain altitudes. Terraforming their moons, such as Europa or Titan, could create habitable environments shielded from radiation by the gas giant's magnetic field. This approach broadens the scope of terraforming, focusing on unconventional environments. A magnetic field is essential for protecting a planet's atmosphere from stellar winds and radiation. For planets lacking natural magnetic fields, artificial solutions could include electromagnetic generators, large-scale systems that create a planetary magnetosphere to shield the surface from harmful radiation. Alternatively, molten core stimulation, inducing convection in a planet's core through tidal heating or nuclear techniques, could generate a natural magnetic field. Building magnetic fields is a long-term solution, but critical for maintaining atmospheric stability on terraformed planets. Plate tectonics play a vital role in recycling nutrients and regulating atmospheric composition. On geologically inactive planets, this process could be jump-started by artificial seismic activity, using controlled explosions to create tectonic motion. Injecting heat into the mantle through nuclear or geothermal techniques could reignite volcanic activity. Mass redistributors, such as orbital tethers or artificial satellites, could create gravitational stresses to simulate tectonic motion. Reviving tectonic activity ensures long-term ecological balance, crucial for sustaining life. The introduction of life to a terraformed planet would require tailored ecosystems. Microbial pioneers, such as genetically engineered bacteria, could adapt to the planet's unique chemistry, initiating oxygen production or soil formation. Hardy plants, designed to survive in extreme conditions, could establish the first vegetation cover, stabilizing the atmosphere and enriching the soil. Synthetic animals, engineered for specific ecological roles, might follow to maintain balance and provide resources for human settlers. This bioengineering approach ensures that life can take root even in challenging environments. For planets slightly outside the habitable zone, altering their orbit could bring them closer to or farther from their star. Using gravity assists with nearby moons or planets, or deploying artificial structures like solar sails to apply gradual force, could adjust the planet's orbit into a more favorable position. These ambitious techniques demonstrate the scale of engineering required for terraforming. Super-Earths, while promising due to their size and gravity, present unique challenges. Their thicker atmospheres may trap heat or block sunlight, requiring extensive atmospheric thinning. High gravity makes moving resources or constructing large-scale infrastructure more difficult. Strong tectonic activity could create unstable surface conditions. Despite these challenges, their long-lived geological activity and potential for retaining water make them intriguing candidates for terraforming. The ethics of terraforming raise profound questions. Should humanity transform alien ecosystems, potentially destroying native microbial life in the process? Does altering a planet's natural state impose a form of cosmic colonization, disregarding its intrinsic value? Should resources be devoted to terraforming when Earth itself faces significant environmental challenges? Balancing ambition with responsibility will be crucial as terraforming technologies advance. Given the immense complexity of terraforming, artificial intelligence, AI, and automation will likely play a central role. Autonomous robots could perform tasks like seeding microbes, constructing infrastructure, or monitoring atmospheric changes. AI algorithms could simulate planetary ecosystems, predicting the outcomes of terraforming efforts and identifying potential pitfalls. Automated systems could operate over centuries, maintaining terraforming projects far beyond human lifespans. AI-driven terraforming represents the intersection of cutting-edge technology and interstellar ambition. Terraforming exoplanets offers humanity a vision of the future where the boundaries of Earth are no longer the limits of life. It promises to expand our reach across the stars, transforming hostile worlds into thriving habitats. Yet, it also demands unprecedented technological advancements, astronomical resources, and profound ethical reflection. As we explore the possibilities of terraforming, we must remember the lessons of Earth, our only known habitable planet. By preserving and cherishing our home, we gain the wisdom to approach terraforming with respect, innovation, and a sense of shared purpose. Stellar influence. How stars shape exoplanet. Habitability. Stars are the lifeblood of planetary systems. They provide the light and heat that make planets habitable, sculpt their orbits, and influence the development of atmospheres and climates. Yet not all stars are created equal. The type, size, activity, and life cycle of a star profoundly affect the potential for its planets to support life. The concept of a habitable zone, the region around a star where conditions might allow liquid water to exist, is central to assessing habitability. For Sun-like stars, the habitable zone lies at a moderate distance, encompassing planets like Earth and potentially Mars in the past. Around red dwarfs, which are cooler and dimmer, the habitable zone is much closer, often placing planets at risk of tidal locking and stellar flares. In contrast, blue giants and other high-mass stars have wider habitable zones, but their short lifespans limit the time available for life to evolve. The Goldilocks principle emphasizes that the right amount of heat and light is essential for sustaining life. A star's lifespan dictates the window of opportunity for life to emerge and thrive. Red dwarfs, with lifespans exceeding trillions of years, offer long-term stability for planets in their habitable zones, despite their high activity in early stages. Sun-like stars, G-type stars, provide billions of years of steady energy output, long enough for complex ecosystems to develop. Massive stars, such as O-type and B-type, burn out quickly, often within a few million years, leaving little time for life to gain a foothold. The longevity of a star sets the evolutionary pace for its planetary system. Stars are not passive players in their planetary systems. Their activity can either nurture or devastate planetary environments. Young stars, regardless of type, are often highly active, emitting intense stellar flares and solar winds that can strip atmospheres from nearby planets. Red dwarfs are notorious for their flare activity, which may sterilize planets in close orbits despite their long lifespans. Conversely, stable stars with low variability provide the consistency needed for ecosystems to flourish. While stellar activity poses challenges, it also drives chemical reactions in planetary atmospheres, potentially fostering prebiotic chemistry. The metallicity of a star, its abundance of elements heavier than hydrogen and helium, plays a crucial role in the formation of planets. High metallicity stars are more likely to host rocky planets, as metals are essential for building planetary cores. Low metallicity stars often form systems dominated by gas giants or icy bodies, with fewer terrestrial planets. The metallicity of a star provides a snapshot of its galactic neighborhood, linking planet formation to the broader history of the cosmos. Planets orbiting binary star systems face unique challenges and opportunities. Circumbinary planets like Kepler-16b orbit both stars and experience dynamic illumination patterns as the stars move relative to one another. Close binary stars may eject or destabilize planets in chaotic gravitational interactions, limiting the formation of stable orbits. Wide binary systems allow for more predictable orbits, potentially creating environments where life could develop. Binary systems add complexity to the habitability equation, creating both risks and opportunities for life-bearing planets. As stars evolve, their energy output changes, causing their habitable zones to shift. Young stars gradually brighten, pushing the habitable zone outward over billions of years. Planets that were once too cold may enter the habitable zone later in their star's life, as seen in the case of Mars, if the Sun continues to warm. Dying stars, such as red giants, expand their habitable zones temporarily, potentially warming distant icy worlds before they are engulfed. These fluctuations provide windows of opportunity for habitability, albeit often brief and challenging. The habitable zones of red dwarfs are so close to the star that planets within them are often tidally locked, with one side perpetually facing the star and the other in eternal darkness. The star-facing side risks overheating, while the dark side may freeze solid. However, atmospheric circulation could distribute heat, creating a temperate zone at the boundary between light and dark, known as the terminator zone. Tidally locked planets around red dwarfs offer unique environments for habitability, requiring further study to assess their potential. Ultraviolet, UV radiation from a star has a significant impact on planetary atmospheres and surface conditions. Moderate UV radiation can drive prebiotic chemical reactions, such as the formation of amino acids, essential for life. Excessive UV radiation can strip atmospheres and sterilize planetary surfaces, as seen on Proxima Centauri b, due to its flaring host star. The balance of UV radiation is a critical factor in determining whether a planet can support life. Even after a star's death, it may still influence the habitability of its planets. Planets orbiting white dwarfs, the remnants of low and medium mass stars, might experience temporary habitability as the star cools. The habitable zone around a white dwarf is much closer, making these systems vulnerable to tidal forces and stellar radiation. While short-lived, these environments offer a glimpse into the resilience of planetary systems. Magnetic interactions between a star and its planets can have profound effects on habitability. Planets with magnetic fields are better protected from stellar winds, preserving their atmospheres over billions of years. Magnetic fields also create auroras, which can serve as indirect indicators of a planet's ability to sustain life. Understanding these interactions helps scientists assess the long-term habitability of planets in different stellar environments. One of the most unusual planetary systems involves planets orbiting pulsars, the remnants of massive stars. Pulsar planets, such as those around PSRB 1257+12, are bombarded with intense radiation and energetic particles. Despite these hostile conditions, the discovery of such planets challenges our understanding of where planets can form and survive. Pulsar planets highlight the extremes of planetary evolution and the resilience of celestial bodies. The location of a star within the galaxy also influences its planet's habitability. Stars near the galactic center are exposed to higher levels of radiation and gravitational disturbances, reducing the likelihood of habitable planets. Stars in the galactic habitable zone, a region with moderate metallicity and fewer supernova events, are more likely to host stable, life-friendly systems. The galactic environment adds another layer of complexity to the search for habitable worlds. Advances in technology and observation are enabling scientists to study star-planet interactions in unprecedented detail. Missions like the James Webb Space Telescope, JWST, and Plato are designed to analyze the atmospheres and orbital dynamics of exoplanets around different types of stars. The development of stellar spectropolarimetry will allow scientists to better understand the magnetic fields and activity cycles of stars, key factors in assessing habitability. As our understanding of stars deepens, so too does our ability to evaluate the potential for life in their planetary systems. The relationship between stars and their planets is a cosmic dance, a delicate interplay of forces that shapes the potential for life. From the comforting stability of sun-like stars to the volatile extremes of red dwarfs and the fleeting opportunities of white dwarfs, stars are the architects of habitability. By studying the stars, we gain insights not only into the nature of exoplanets, but also into the conditions that made life on Earth possible. Exotic weather patterns, the extreme climates of alien worlds. Weather on Earth is a complex interplay of atmospheric pressure, temperature, and moisture. Yet compared to the conditions on many exoplanets, our storms and winds are tame. The alien climates discovered in distant star systems push the boundaries of imagination, with phenomena so extreme they defy earthly logic. From glass rain and supersonic winds to endless hurricanes and methane snow, the weather on exoplanets showcases nature's capacity for diversity and extremes. This section dives into some of the most extraordinary weather patterns known to science, exploring how they form and what they reveal about these distant worlds. Hot Jupiter HD 189733b, 64 light-years distant, is one of the most famous exoplanets with harsh weather. A violent whirlwind fills this planet's atmosphere. Sideways raining molten glass droplets are created when silicate particles are whipped across the atmosphere by winds reaching 7,000 kilometers per hour. The silicate clouds cast a bluish light across the planet, giving it its eye-catching blue color, a subtle beauty that belies its ferocity. The combination of the star's tremendous heat and the planet's thick atmosphere causes weather conditions that are considerably more severe than anything Earth has ever seen. On some ultra-hot Jupiters, such as WASP 76b, the temperatures are so extreme that metals vaporize and rain back down. Dayside temperatures exceed 2,400 degrees Celsius, hot enough to vaporize iron. Strong winds carry the iron vapor to the cooler night side, where it condenses into droplets and rains down in a metallic deluge. This iron rain creates a surreal weather system that highlights the extremes of heat redistribution on tidally locked planets. Colder exoplanets, especially those orbiting farther from their stars, often host weather systems dominated by hydrocarbons. On planets like GJ 1214b, clouds of methane and ethane form in the upper atmosphere, creating methane snowstorms that blanket the surface. These hydrocarbons reflect starlight, making such planets appear bright even from vast distances. Methane-rich environments are thought to resemble Titan, Saturn's largest moon, offering analogues for studying exotic weather patterns. Tidally locked exoplanets, with one side always facing their star and the other in perpetual darkness, exhibit unique weather phenomena. The intense heat on the day side causes air to rise and flow toward the cooler night side, creating constant superstorms at the terminator zone. These storms often take the form of perpetual hurricanes, driven by extreme temperature contrasts. Models suggest these storms could create regions of relative stability at the eye of the hurricane, offering pockets of potential habitability. On planets like Kepler 10b, with surfaces baked to extremes, the combination of heat and atmospheric pressure can lead to continuous lightning storms. The dense atmosphere generates static electricity as particles collide, creating storms that last for days or even years. Lightning on such planets may involve exotic compounds, like sulfur or silicon, producing colors and patterns unseen on Earth. These eternal thunderstorms are not just violent, but may also play a role in atmospheric chemistry, shaping the planet's long-term climate. Some exoplanets, particularly hot Jupiters, are veiled by high-altitude silicate clouds. These clouds reflect light, making the planets appear brighter than they should given their proximity to their stars. On Kepler 7b, these clouds are concentrated on the planet's western hemisphere, creating uneven heating and circulation patterns. Silicate clouds are a hallmark of extreme atmospheric temperatures, adding a layer of complexity to the study of exoplanet climates. Exoplanets with eccentric orbits often experience wild swings in temperature as they move closer to or farther from their stars. HD 80606b, for instance, undergoes temperature changes of over 1000 degrees Celsius during its 111-day orbit, with brief periods of intense heating followed by long freezes. Such variations create dramatic weather cycles, including sudden storms and massive shifts in atmospheric pressure. These temperature extremes offer insights into the adaptability of planetary atmospheres under changing conditions. On planets with thick atmospheres and high temperatures, winds often reach supersonic speeds. Hot Jupiters like Upsilon Andromedae b experience wind speeds of up to 20,000 kilometers per hour, redistributing heat from their day side to their night side. These winds can carry gases and aerosols across the planet, creating turbulent weather systems that defy earthly comparison. Supersonic winds demonstrate the raw power of atmospheric dynamics on massive exoplanets. Some exoplanets resemble Venus, where a runaway greenhouse effect traps heat and creates hellish conditions. Planets like Kepler 1649c, which lie on the inner edge of their habitable zones, may experience extreme warming as water vapor amplifies the greenhouse effect. Over time, these planets could become entirely uninhabitable, with thick atmospheres of carbon dioxide and sulfuric acid clouds. Studying runaway greenhouse effects offers cautionary lessons about the fragility of planetary climates. Some planets, like Kepler 10c, exhibit exceptionally high albedo, reflecting much of the light they receive. These planets are often covered in clouds or icy surfaces that bounce starlight back into space, creating cooler than expected climates. High albedo planets are easier to detect and study because their brightness makes them stand out against their stars. These reflective worlds challenge assumptions about how planets absorb and retain heat. Planets dominated by oceans, water worlds, exhibit unique weather systems shaped by their vast seas. Strong winds and storms whip across the surface with no land masses to disrupt their flow. The absence of land also prevents the formation of dust storms, resulting in smoother but more intense atmospheric circulation. Water worlds provide an extreme contrast to Earth, where the interplay between land and ocean defines weather patterns. On rocky exoplanets with thin atmospheres, dust storms dominate. These storms can envelop the entire planet, as seen on Mars analogues like HD 219134b. Dust plays a crucial role in shaping the planet's climate, reflecting heat back into space or trapping it near the surface. Dust storms highlight the importance of surface composition in determining weather patterns. Planets orbiting binary stars experience irregular heating as they receive light and heat from two sources. The shifting alignment of the stars creates periodic temperature and weather changes, leading to unpredictable climates. Planets in these systems may experience rapid cooling and heating cycles, driving extreme storms and atmospheric turbulence. Binary systems showcase the interplay between stellar dynamics and planetary weather. Understanding the weather on exoplanets is more than a scientific curiosity. It's a window into the forces that shape planetary environments and their potential for life. As telescopes like the James Webb Space Telescope JWST, and the European Extremely Large Telescope, EELT, come online, scientists will be able to map atmospheric patterns, detect exotic clouds, and measure temperature gradients with unprecedented precision. These studies not only reveal the diversity of weather across the cosmos, but also provide insights into the fragility and resilience of climates, including our own. The weather on alien worlds reminds us that nature operates on a vast spectrum, creating conditions that challenge our understanding and fuel our imagination. Alien ecosystems, speculative biology on exoplanets. Life on Earth is diverse, resilient, and astonishingly adaptable. From bacteria thriving in deep-sea hydrothermal vents to plants photosynthesizing in sunlight, Earth's ecosystems provide a blueprint for how life might develop elsewhere. But on exoplanets, worlds shaped by unfamiliar physics, chemistry, and climates, life could take forms we can scarcely imagine. This section delves into speculative biology, exploring how alien ecosystems might adapt to the unique conditions of their worlds, and how these adaptations could expand our understanding of life's possibilities. Photosynthesis on Earth depends on visible light, but the light available on exoplanets can vary dramatically. Around red dwarf stars, which emit mostly infrared light, photosynthesis might shift to absorb longer wavelengths. Alien plants could be black, deep red, or even transparent to maximize energy capture. Conversely, on planets orbiting blue stars, high-energy ultraviolet light might drive a different kind of photosynthesis, leading to organisms with reflective, iridescent surfaces to protect against radiation. This diversity in stellar light could produce ecosystems as varied in color and structure as coral reefs or rainforests on Earth. Gas giants, with their dense atmospheres and crushing cores, seem inhospitable. Yet at certain altitudes, conditions might allow life to thrive. Floating organisms similar to jellyfish or ballooning spiders could drift on buoyant sacs filled with lighter gases like hydrogen or methane. Microbial colonies might form in dense cloud layers, feeding on chemical energy from atmospheric reactions. These aerial ecosystems could resemble swarms of plankton, living in a three-dimensional environment defined by turbulent winds and chemical gradients. On water worlds and icy moons, life could exist in vast subsurface oceans beneath kilometers of ice. Without sunlight, ecosystems might depend on hydrothermal vents, where chemical energy from the planet's interior powers microbial life. Complex organisms could evolve near these vents, developing adaptations like heat-resistant shells or chemical sensors to locate food in the dark. Such ecosystems might resemble Earth's deep-sea communities, with creatures like tube worms, crabs, and bioluminescent fish. The gravity of an exoplanet shapes the size, form, and movement of its organisms. On low-gravity worlds, creatures might grow taller or develop balloon-like appendages to aid in movement or energy capture. Trees could tower to incredible heights, while animals might glide or hover effortlessly. On high-gravity planets, life forms would likely be squat, compact, and muscular to counteract the stronger pull. Plants might grow low to the ground, with dense structures to resist gravity's force. The interaction between gravity and biology leads to ecosystems uniquely tailored to their environments. Life as we know it is carbon-based and depends on water. But on alien worlds, alternative biochemistries could arise. On Titan-like planets, where methane replaces water, life might use hydrocarbons as a solvent, operating at much lower temperatures with slower metabolisms. Silicon-based life, while speculative, could thrive in hotter environments, forming structures resistant to extreme heat. Exploring alternative chemistries broadens the scope of what life could look like, challenging our Earth-centric assumptions. On exoplanets with extreme climates, symbiosis could be key to survival. Organisms might form mutualistic relationships, such as photosynthetic animals, where one organism provides energy through photosynthesis, while another offers mobility or protection. On tidally locked planets, creatures from the hot side might migrate to the cold side, carrying thermal energy or nutrients back in a planetary scale exchange system. Symbiotic adaptations demonstrate how life might creatively exploit challenging environments. Planets without sunlight, such as rogue planets or those with thick, light-blocking atmospheres, could still harbor life. Chemosynthetic organisms might use chemical reactions to produce energy, similar to microbes near Earth's hydrothermal vents. Ecosystems might develop around geothermal hotspots, with organisms clustering near sources of heat and nutrients. Life in perpetual darkness would evolve senses and communication methods adapted to their shadowy world, perhaps relying on sound, heat, or electric fields. Exoplanets with eccentric orbits, where temperatures fluctuate wildly, could host highly adaptive ecosystems. Organisms might enter states of dormancy during freezing periods, similar to Earth's tardigrades or Arctic frogs. Plants could evolve to store energy during brief warm periods, surviving long winters in a hibernation-like state. These dynamic ecosystems would demonstrate resilience and innovation in the face of extreme environmental changes. Predation and competition are universal drivers of evolution, but the rules could change dramatically on alien worlds. On high-gravity planets, predators might rely on ambush tactics rather than speed, using camouflage or environmental traps. On water worlds, predators could develop bioluminescent lures to attract prey in the darkness of the deep ocean. These dynamics would shape the structure and behavior of alien ecosystems, creating niches and food webs distinct from those on Earth. Planets with strong magnetic fields might influence the evolution of life. Magnetotactic bacteria on Earth use magnetic fields for navigation. Similar organisms could evolve on alien planets with stronger fields. Large animals might develop sensory organs that detect magnetic fields, aiding migration or hunting in environments with limited visibility. Magnetic fields could become a fundamental part of an alien planet's ecological framework. On planets with polar orbits, ecosystems might experience dramatic seasonal variations as the planet tilts toward and away from its star. Organisms could evolve to take advantage of long periods of daylight, growing rapidly during summers and hibernating during extended winters. Migratory behaviors might dominate, with species following light and warmth around the planet. Polar orbits create ecosystems that are cyclically dynamic, with life adapting to the rhythm of extreme seasons. While microbial and plant-like organisms are more likely, the evolution of intelligent life on exoplanets remains a possibility. On water worlds, intelligent life might develop tools and communication systems adapted to underwater environments, such as echolocation or bioluminescent signals. On planets with multiple moons or rings, advanced species might evolve a deep understanding of celestial mechanics, influencing their culture and technology. Intelligent life would likely reflect its planet's unique conditions, offering a diversity of perspectives and possibilities. Binary star systems provide unique lighting conditions that could shape ecosystems. Plants might evolve to follow multiple light sources, with leaves that reorient as the stars move through the sky. Predators and prey might adapt to irregular light cycles, developing enhanced night vision or heat-sensing abilities. Binary star systems create an environment of constant change, driving the evolution of highly flexible and adaptive ecosystems. In ecosystems where traditional senses are less effective, organisms might rely on bioelectricity. Electric fields could be used for hunting or navigation, similar to electric eels or sharks on Earth. Communication through electrical signals might evolve, allowing species to speak through flashes of light or pulses. This form of interaction would create ecosystems where electrical activity is as important as sound or sight. Speculating about alien ecosystems is not just an exercise in imagination, it's a way to expand our understanding of life's potential. The creatures and ecosystems that might exist on exoplanets challenge us to think beyond Earth's constraints, exploring new forms of biology, chemistry, and behavior. Habitability in binary star systems. Life under two suns. Binary star systems, where two stars orbit a common center of mass, are among the most fascinating environments in the cosmos. Nearly half of the stars in the Milky Way are part of binary or multi-star systems, making them a significant focus in the search for habitable exoplanets. The presence of two suns offers unique opportunities and challenges for planetary habitability, creating dynamic environments that stretch our understanding of life's potential. From shifting habitable zones to complex orbital dynamics, binary star systems reveal the cosmic dance of dual suns and their profound influence on planets. Binary star systems come in a variety of configurations, each with distinct implications for planetary habitability. Close binaries involve stars orbiting each other at close distances, often with periods of days or weeks. Planets in these systems typically orbit far enough away to encompass both stars. Wide binaries feature stars separated by vast distances, with planets orbiting one star while experiencing gravitational influences from the other. Circumbinary systems have planets orbiting both stars in a single wide orbit, as seen in the famous Kepler-16b system. Each configuration offers unique opportunities for stable orbits, light availability, and temperature regulation. The habitable zone in binary systems is more complex than around single stars, as the gravitational and luminous interactions between the stars influence where life-sustaining conditions might arise. In circumbinary systems, the habitable zone shifts as the two stars move in their orbits, creating fluctuating temperatures on the planet. In wide binaries, the secondary star's radiation can periodically alter conditions on the planet, adding additional variability. These shifting zones create dynamic environments where adaptability might be a key trait for any potential life forms. Binary stars create unique illumination patterns that could profoundly impact planetary climates. Planets in circumbinary orbits experience dual sunrises and sunsets, with varying intensities of light depending on the relative positions of the stars. For planets orbiting a single star in a wide binary system, the secondary star may appear as a bright point in the sky, providing additional but weaker light. These patterns could influence the development of photosynthetic life, which might adapt to varying intensities and spectral qualities of light. The stability of a planet's orbit is a critical factor in its habitability. In close binary systems, gravitational perturbations can destabilize planetary orbits, ejecting planets from the system or sending them into highly elliptical paths. In circumbinary systems, planets must maintain a safe distance from the binary pair to avoid chaotic gravitational forces. This creates a safe zone where orbits remain stable over billions of years. Stable orbits are essential for maintaining consistent conditions that allow life to evolve and thrive. The complex gravitational forces in binary systems can generate tidal heating on planets and moons. Planets in eccentric orbits may experience significant tidal stress, heating their interiors and potentially creating subsurface oceans, as seen on moons like Europa and Enceladus in our solar system. This tidal heating could create localized hotspots, providing energy for life even in regions outside the traditional habitable zone. Gravitational interactions thus add a layer of complexity to the search for habitable environments. Stars in binary systems often exhibit higher levels of activity due to their mutual gravitational influences. Magnetic interactions between close binary stars can amplify stellar flares, which release bursts of radiation that can strip planetary atmospheres or sterilize surfaces. Circumbinary planets are somewhat shielded from these effects, as their orbits often place them farther from the stars. Understanding the variability of stellar activity is crucial for assessing the long-term habitability of planets in binary systems. Planets in binary systems experience unique climate variations due to the combined effects of their stars. Dual stars can create dual seasonal cycles, with temperature fluctuations influenced by both the relative positions of the stars and the planet's orbit. In circumbinary systems, irregular heating patterns can lead to extreme weather, such as prolonged winters or intense storms during periods of dual solar alignment. These climatic dynamics could shape ecosystems and drive evolutionary adaptations in unexpected ways. The presence of two stars offers unique opportunities for photosynthetic organisms. Plants might evolve pigments optimized for both stars' spectral outputs, creating a greater diversity of photosynthetic mechanisms. In systems with a bright primary star and a dimmer companion, photosynthesis might rely on the primary star for high-energy processes while using the secondary star for low-energy functions. Binary star systems expand the potential strategies for light-dependent life forms. The diversity of light, climate, and gravitational conditions in binary systems could foster complex ecosystems. Dual illumination could lead to unique flora and fauna adapted to fluctuating energy inputs, such as plants with reversible pigmentation or animals with seasonal migration patterns based on stellar alignments. Extreme climate variations might encourage resilience and adaptability, driving rapid evolution and diversification of life forms. Binary systems could thus serve as natural laboratories for studying the limits of ecological complexity. The gravitational interplay in binary systems affects a planet's ability to retain water. Planets in close binary systems are more likely to experience water loss due to intense radiation and tidal heating. In circumbinary systems, the wider orbits reduce the likelihood of water evaporation, preserving conditions favorable for life. Understanding water retention in these systems is critical for identifying promising targets in the search for habitable worlds. Several binary star systems have yielded intriguing planetary discoveries. Kepler-16b is a circumbinary planet with a stable orbit around two stars, demonstrating that planets can exist in dynamic systems. Kepler-47c is a gas giant in the habitable zone of a circumbinary system with the potential for habitable moons. The Alpha Centauri system, the closest star system to Earth, features a binary pair, Alpha Centauri A and B, and the planet Proxima Centauri b, a potential candidate for life. These systems highlight the diversity and potential of binary star environments. The unique conditions in binary systems might influence the development of intelligent life. The variability of light and climate could drive technological innovation as intelligent species adapt to fluctuating environments. The presence of two stars might inspire unique cultural and philosophical perspectives, shaping civilizations in ways we cannot predict. Binary systems thus offer not just scientific intrigue, but also the potential for entirely new ways of understanding life and intelligence. Binary star systems are among the most dynamic and challenging environments for life, but they also offer extraordinary opportunities. Their unique illumination patterns, shifting habitable zones, and gravitational interactions create conditions unlike any seen in single-star systems. These systems stretch the boundaries of habitability, demonstrating nature's ability to adapt and thrive under even the most complex circumstances. The hunt for life will continue to center on binary star systems, which show the vast variety of possible habitats for life. The idea of subsistence under two suns is more than a science fiction fantasy. It's an exciting new frontier. Rogue planets, wandering worlds without a star. Not all planets are bound by the gravitational pull of a star. Rogue planets, also known as free-floating planets, wander the cosmos untethered, drifting through the dark expanses of interstellar space. Ejected from their original systems or formed in isolation, these wandering worlds defy conventional notions of planetary habitability, yet they offer unique opportunities for scientific exploration and perhaps even the potential for life. Rogue planets are enigmatic and challenging to study, but their sheer abundance and mysterious nature make them one of the most intriguing phenomena in modern astronomy. Rogue planets are planetary mass objects that do not orbit a star. Instead, they drift freely through interstellar space, unbound by the gravity of any stellar system. Their origins may involve planetary ejection, where gravitational interactions during the chaotic early stages of planetary system formation can eject planets into space. Alternatively, isolated formation occurs when rogue planets form directly from collapsing clouds of gas and dust, similar to stars, but fail to ignite nuclear fusion. These planets are diverse in size and composition, ranging from rocky Earth-like bodies to massive gas giants. The origins of rogue planets are varied and complex. In gravitational ejection, young planetary systems experience close encounters between planets or interactions with a passing star, which can fling planets into interstellar space. Starless formation allows rogue planets to arise in dense molecular clouds, forming like stars, but without the mass to initiate fusion. Additionally, collapse of protoplanetary disks might lead to the direct formation of rogue planets, bypassing traditional star-centered planetary system development. These mechanisms highlight the diversity of pathways leading to rogue planet formation. Astronomers estimate that rogue planets may outnumber stars in the Milky Way. Studies using microlensing techniques have identified Jupiter-sized rogue planets in interstellar space, suggesting that the galaxy could host billions of such objects. While smaller, Earth-sized rogue planets are harder to detect, statistical models predict they may be even more abundant. If true, rogue planets could represent a significant, yet largely unexplored population of planetary bodies in the galaxy. Rogue planets are notoriously difficult to detect due to their lack of a host star. Detection methods include microlensing, where a rogue planet's gravity bends and magnifies the light of a distant star, creating a brief, detectable brightening event. Infrared emissions from residual heat, left over from their formation, can also reveal rogue planets, while direct imaging may eventually capture larger rogue planets with thick, heat-trapping atmospheres. Despite these challenges, advancing technology is improving the feasibility of rogue planet detection. Rogue planets exist in some of the harshest conditions imaginable. In perpetual darkness, they lack sunlight, making photosynthesis impossible and rendering their surface temperatures frigid. Extreme cold drives surface temperatures near absolute zero unless internal heat sources are present. However, atmospheric retention could trap residual heat, preventing the planet from freezing entirely. Despite these challenges, certain factors might allow rogue planets to host life. While rogue planets seem inhospitable, some conditions might support life. Geothermal heating from residual formation heat or radioactive decay in the core could sustain subsurface oceans, much like Europa or Enceladus in our solar system. Thick atmospheres, particularly those rich in hydrogen, could insulate the planet, maintaining temperatures suitable for liquid water. Additionally, exotic energy sources like chemosynthesis could replace photosynthesis, allowing life to thrive in subsurface ecosystems. Life on rogue planets would likely resemble extremophiles on Earth, capable of surviving in conditions far removed from those found on Earth. Rogue planets with subsurface oceans offer one of the most plausible habitats for life. These oceans might remain liquid due to heat from the planet's core, driven by radioactive decay, or tidal heating if the planet retains any moons. Subsurface ecosystems could mirror those under Antarctic ice or in Earth's deep oceans, where light is absent but life thrives around hydrothermal vents. These hidden oceans represent a promising avenue for exploring life's adaptability. The presence of a thick atmosphere could significantly enhance the habitability of rogue planets. Hydrogen-rich atmospheres act as excellent insulators, trapping heat and maintaining temperatures that allow liquid water to exist. Atmospheric chemistry might include gases like methane or ammonia, supporting exotic life forms adapted to these environments. The ability to retain such atmospheres depends on a planet's size, gravity, and distance from sources of radiation or stellar winds. Even rogue planets can tell us a little bit about their home systems. It is possible that the composition and history of a planet's system can be preserved in its rocks, minerals, and atmospheric components. As time capsules from their formation conditions, some rogue planets may even contain organic molecules or microbes. Investigating these worlds may provide light on the evolution of planetary systems and the dispersion of organic substances throughout the galaxy. Rogue planets might one day serve as stepping stones for human expansion into interstellar space. Subsurface bases could be established beneath insulating layers of ice or rock, tapping into geothermal heat and extracting water from subsurface reservoirs. Hydrogen mining from thick hydrogen atmospheres could provide resources for fuel and energy. With advanced technology, self-sustaining ecosystems might make rogue planets viable as long-term habitats. While challenging, the colonization of rogue planets represents an intriguing possibility for the future of space exploration. Rogue planets may act as waypoints for interstellar travel, offering potential refueling or resupply stations for long-distance missions. Their abundance suggests they might be relatively evenly distributed throughout the galaxy, making them practical checkpoints for advanced propulsion systems like nuclear fusion or antimatter drives. Their isolation also makes them ideal testbeds for developing self-sufficient technologies. Rogue planets with moons could experience tidal heating, creating additional energy sources. Tidal interactions might generate internal heat, driving geological activity and maintaining subsurface oceans. Moons could also serve as material sources for mining or scientific study, enhancing the habitability and scientific value of these planets. Some theories suggest rogue planets might interact with dark matter in unique ways. As they drift through interstellar space, rogue planets could collect dark matter in their cores, creating subtle anomalies in their heat signatures. These interactions could provide a novel method for studying dark matter, offering a potential intersection between planetary science and cosmology. Their boundless nature gives them an air of mystery and potential, while also making them difficult to examine. A rogue planet is a reminder that the universe is full of surprises, whether it's a microbiological sanctuary, a remnant of a former planetary system, or a potential landing site for astronauts. Exoplanetary rings, silent sculptors of planetary systems. In the cosmic theater of planetary systems, exoplanetary rings stand as silent yet powerful players. Often overshadowed by their host planets and moons, these massive luminous structures serve as dynamic forces that shape their environments in profound and often overlooked ways. From their influence on climate and habitability to their role as historical archives of planetary systems, exoplanetary rings weave a complex narrative of creation, destruction, and cosmic balance. Alterations to the host planet's weather are among the most fascinating ring effects. The planet's rings reroute energy by reflecting and scattering starlight, much like gigantic space mirrors. The environmental effects of this dispersion may be rather noticeable and include things like the extension of twilight or the formation of colder zones by means of extended shadows. Planets with rings around them may be able to moderate their most severe temperatures, making them more hospitable to life. Seasonal changes amplify the interaction between light and shadow, providing an intriguing opportunity to investigate how these structures may create distinct, life-supporting environments. Imagine a planet with a dense ring system casting shimmering bands of light onto its surface, subtly shaping its ecosystems. Extended twilight periods could alter photosynthesis cycles, giving rise to plant life adapted to varying light intensities. The reflective properties of rings could also shield planets from excessive stellar radiation, acting as a natural sunscreen for potentially habitable worlds. Exoplanetary rings serve as cosmic diaries, recording the tumultuous histories of their systems. Their origins often lie in catastrophic events: a disintegrated moon torn apart by tidal forces, a massive collision between celestial bodies, or debris from comets and asteroids captured by the planet's gravity. The size, composition, and structure of rings can reveal critical details about these ancient upheavals. For instance, narrow, well-defined rings might suggest the presence of shepherd moons, small satellites that maintain the ring's shape through their gravitational influence. On the other hand, diffuse or irregular rings could point to more recent chaotic events. Studying these rings allows astronomers to reconstruct the violent processes that sculpt planetary systems, shedding light on the forces that ultimately shape habitability. Detecting rings around exoplanets is no small feat. Unlike the spectacular visibility of Saturn's rings in our solar system, Exoplanetary rings are faint and distant, requiring innovative methods to uncover their presence. One of the most promising techniques involves analyzing transit light curves. As a planet with rings passes in front of its star, the rings create distinctive patterns of dimming, betraying their existence. These patterns are often irregular, hinting at the unique shape and density of the rings. Another method involves gravitational microlensing, where the alignment of a star, planet, and its rings magnifies and distorts the star's light. This technique offers tantalizing glimpses of rings that might otherwise remain hidden. Advances in spectroscopy also promise to reveal the chemical composition of rings, detecting the presence of water ice, organic molecules, and rocky debris. Beyond their visual and scientific allure, exoplanetary rings hold the potential to serve as invaluable resource reservoirs. Rich in water ice, metals, and silicates, these rings could be a treasure trove for future space exploration. For instance, mining operations on rings might extract essential materials for building spacecraft or sustaining off-world colonies. The astrobiological implications are equally fascinating. Rings may occasionally deposit water and organic materials onto their host planets, acting as cosmic delivery systems that enhance habitability. Such material transfer could play a crucial role in jump-starting prebiotic chemistry, providing the essential building blocks for life. The relationship between rings and moons is one of mutual influence, with profound consequences for both. Rings often coexist with intricate moon systems, each sculpting the other through gravitational interactions. Shepherd moons are particularly notable for their role in maintaining the sharp edges of rings, preventing material from dispersing into space. Conversely, moons may owe their very existence to ring systems. Over time, the accumulation of material within rings can coalesce into moonlets, which either remain within the ring or migrate outward to become independent satellites. The dynamic interplay between these celestial companions underscores the interconnectedness of planetary systems. Not all rings are destined to endure. Some are fleeting, formed by transient events like asteroid impacts or cometary debris. These short-lived rings gradually disperse, their material either falling onto the planet or escaping into space. Others, like Saturn's majestic rings, may persist for billions of years, stabilized by the planet's gravity and shepherd moons. The longevity of a ring system often depends on its mass and composition. Massive, icy rings are more likely to endure, while lighter, dust-dominated rings are susceptible to solar radiation and dispersal. Understanding the life cycles of rings provides critical insights into the evolution of planetary systems. Rings don't just shape the space around them, they also influence the weather and tides of their host planets. By casting shadows and reflecting light, rings can create localized cooling or warming effects, altering atmospheric circulation and precipitation patterns. Such modifications might give rise to unique weather phenomena, like prolonged jet streams or alternating bands of rain and drought. The gravitational impact of rings also extends to tidal forces. Rings contribute to a planet's overall gravitational field, affecting the tides experienced by its oceans and the geological activity of its moons. Enhanced tidal heating, driven by the combined forces of the planet and its rings, could create hotspots of volcanic and hydrothermal activity, fostering environments where life might emerge. Despite their dramatic impact, extensive ring systems like Saturn's are relatively rare. Most exoplanets lack detectable rings, raising questions about the specific conditions required for their formation and persistence. One explanation lies in the gravitational and material constraints that govern ring stability. Planets need a delicate balance of mass, proximity to their star, and an abundance of debris to form and maintain rings. Another factor is the age of the planetary system. Rings are more likely to be observed around younger planets, where material from recent collisions or disintegrated moons remains abundant. Older systems may have lost their rings to processes like erosion, accretion, or migration of material into the planet's atmosphere. The future of exoplanetary ring research is bright thanks to advancing technology and observational techniques. Next-generation telescopes like the James Webb Space Telescope, JWST, and the Extremely Large Telescope, ELT, promise to refine ring detection methods, offering unprecedented clarity and precision. These instruments could resolve the fine structure of rings, revealing their composition and dynamics in exquisite detail. Space-based observatories like LISA, Laser Interferometer Space Antenna, may also play a role by detecting gravitational perturbations caused by massive ring systems. Meanwhile, theoretical models are being developed to simulate exotic rings, such as those composed of electrically charged particles or dark matter. Galactic habitable zones, life on a galactic scale. The concept of a habitable zone is often applied to individual stars and their planetary systems. However, just as planets have regions conducive to life, entire galaxies have areas where conditions may be more favorable for the emergence and sustenance of life. These regions, known as galactic habitable zones, GHZs, are shaped by a complex interplay of stellar density, metallicity, radiation, and cosmic events. The galactic habitable zone is the region of a galaxy where conditions are most likely to support habitable planets and the development of life. It represents an area with the right balance of metallicity, stellar density, and radiation exposure. The GHZ is not static. It evolves over time as galaxies grow, merge, and form new stars. For the Milky Way, the GHZ is thought to lie between 7 and 10 kiloparsecs from the galactic center, encompassing the Sun's position. Metallicity, the abundance of elements heavier than hydrogen and helium, is a key factor in defining the GHZ. High metallicity regions, such as the galactic center, are rich in heavy elements necessary for forming rocky planets. However, these areas often have high stellar densities and intense radiation, which can destabilize planetary systems. Low metallicity regions, such as the galactic outskirts, lack the raw materials needed for planet formation, limiting the number of habitable worlds. The GHZ balances these extremes, offering sufficient metals for planet formation without the hazards of high-density regions. The density of stars in a region influences the gravitational stability of planetary systems. In the galactic core, stars are packed tightly, increasing the likelihood of close encounters that can disrupt planetary orbits or eject planets from their systems. In the outer regions, stars are spaced farther apart, reducing these risks but also limiting the gravitational interactions that contribute to planet formation. The intermediate stellar density of the GHZ provides a stable environment for planetary systems to form and evolve over billions of years. Radiation exposure is a critical factor in galactic habitability. Near the galactic center, high-energy events like supernovae and gamma-ray bursts are more frequent, posing threats to planetary atmospheres and surface life. The galactic halo and outskirts are safer from radiation, but lack the metallicity needed for complex planetary systems. The GHZ offers a relatively low radiation environment, minimizing risks while maintaining the conditions necessary for life to develop. The galactic disk, where most of the galaxy's stars and planets reside, plays a central role in the GHZ. The disk contains the bulk of a galaxy's heavy elements, enabling the formation of rocky planets. Its relatively flat structure provides a predictable gravitational environment, reducing the likelihood of catastrophic events like star collisions. The Sun's position within the disk, about 27,000 light-years from the galactic center, places Earth squarely within the GHZ. Certain cosmic events can dramatically affect habitability on a galactic scale. Supernovae release massive amounts of energy and radiation, sterilizing planets within tens of light-years. Gamma-ray bursts, the most energetic events in the universe, can strip away planetary atmospheres even at great distances. Galactic collisions, such as the anticipated merger between the Milky Way and Andromeda, can destabilize entire regions of the galaxy. The GHZ minimizes exposure to these events, providing a safer haven for the development of life. The rate of star formation in a galaxy influences the availability of habitable planets. In regions with rapid star formation, young stars often emit intense radiation that can hinder the development of life on nearby planets. Quieter regions of the galaxy allow for the gradual evolution of planetary systems without the disruptive effects of stellar activity. The GHZ strikes a balance, with a moderate rate of star formation that supports long-term planetary stability. Spiral galaxies, like the Milky Way, feature prominent arms where stars, gas, and dust are concentrated. Spiral arms are regions of active star formation, rich in the heavy elements needed for planet formation. However, their dynamic nature and frequent supernovae make them less hospitable for life compared to the more stable regions between the arms. The Sun's position between two spiral arms, the Perseus arm and the Sagittarius arm, places it in a relatively quiet and stable region of the galaxy. The galactic halo, a sparsely populated region surrounding the disk, offers unique conditions for habitability. The halo contains ancient stars and globular clusters, remnants from the galaxy's earliest epochs. While low in metallicity, some halo stars may host planets formed in the galaxy's core before being ejected into the halo. These ancient systems could harbor long-lived planets, potentially hosting forms of life very different from those on Earth. The GHZ evolves over time as the galaxy changes. Early in a galaxy's history, high radiation levels and low metallicity limited habitability. Over billions of years, star formation and supernovae enriched the galactic disk with heavy elements, expanding the GHZ. Future events, such as galactic mergers, could reshape the GHZ, creating new regions of habitability while disrupting others. The Milky Way's GHZ is currently in its prime, offering optimal conditions for life. Not all galaxies have GHZs identical to the Milky Way's. Elliptical galaxies, with low star formation rates and limited gas, may have narrower GHZs but long-term stability. Irregular galaxies, with their chaotic structures and frequent supernovae, are less conducive to habitability. Dwarf galaxies, while low in metallicity, may offer relative isolation from galactic-scale catastrophes. The structure and dynamics of a galaxy determine the size and characteristics of its GHZ. The Sun's location within the Milky Way offers several advantages for habitability. It lies far enough from the galactic center to avoid the high radiation and gravitational instability of dense stellar environments. Its position between spiral arms reduces the risk of supernova and other catastrophic events. The moderate metallicity of the Sun's neighborhood supports the formation of rocky planets like Earth. These factors collectively make the Sun's position ideal for fostering life. At the crossroads of stellar, planetary, and galactic dynamics lies the galactic habitable zone, an area where all the necessary components for life are present in optimal quantities. It serves as a gentle reminder that in order to determine whether a planet is habitable, one must take into account not just the planet itself, but also the larger cosmic context in which it exists. Star system architecture: how celestial layouts shape planetary worlds. The structure and arrangement of a star system are pivotal in determining the characteristics, stability, and habitability of its planets. From the number and types of stars to the placement of gas giants and asteroid belts, the architecture of a star system creates the conditions that either foster or hinder the development of life. This section examines the diverse architectures of star systems, exploring how their components interact to shape the destiny of planets and moons. Star systems are composed of various elements, each playing a role in the development and habitability of planets. The type, size, and activity of the central star or stars influence the energy and radiation environments, while the planets, varying in size, composition, and distance from the star, are the primary focus in the search for life. Asteroid belts and debris fields serve as reservoirs of materials and can affect planetary surfaces through impacts, and moons, Orbiting planets contribute to tidal forces and may host their own habitable environments. The interplay of these components determines the overall dynamics and potential for habitability in a star system. Single star systems, like our solar system, are often considered the most stable environments for planetary formation. The presence of a single gravitational focus reduces orbital chaos, allowing planets to maintain stable orbits over billions of years. In these systems, planets are more likely to remain within the habitable zone, avoiding destabilizing interactions with a secondary star. The relative simplicity of single-star systems makes them prime targets for studying planetary habitability. Binary and multi-star systems introduce additional complexity. In binary systems, planets may orbit both stars in a wide circumbinary orbit, or one star in a close circumstellar orbit. While stable configurations are possible, gravitational interactions can limit habitability. Multi-star systems with 3 or more stars feature even more intricate gravitational dynamics, often ejecting planets or forcing them into highly eccentric orbits. Despite the challenges, systems like Kepler-16 demonstrate that planets can exist and even thrive in multi-star environments. Gas giants play a crucial role in shaping the architecture of a star system. In systems like ours, gas giants like Jupiter act as shields, deflecting asteroids and comets that might otherwise impact inner planets. Their gravitational influence helps stabilize the orbits of smaller planets and debris, reducing the likelihood of chaotic interactions. However, in some systems, migrating gas giants can disrupt the habitable zone, ejecting rocky planets or bombarding them with debris. The position and behavior of gas giants are critical in determining the long-term stability of planetary systems. Planetary migration significantly influences the final architecture of a star system. Inward migration of hot Jupiters, which form far from their stars and migrate inward, can destabilize inner rocky planets, reducing the chances of habitability. Conversely, outward migration may create gravitational resonances, trapping smaller planets in stable orbits. However, migration often involves chaotic interactions, with planets exchanging angular momentum, leading to collisions or ejections. Migration highlights the dynamic nature of star systems and their potential to evolve significantly after formation. Orbital resonances occur when planets or moons have orbital periods that are simple ratios of one another. These resonances help stabilize orbits, as seen in the Laplace resonance of Jupiter's moons Io, Europa, and Ganymede. In exoplanetary systems, resonances can protect planets from chaotic interactions or create unique orbital dynamics that influence climate and geology. Resonant configurations add a layer of predictability to the otherwise chaotic forces shaping star systems. Asteroid belts serve as both hazards and potential catalysts for life. Impacts from asteroid belts can deliver water and organic materials to young planets, aiding the development of life. However, excessively dense asteroid belts, like those influenced by a close gas giant, can create frequent bombardments, hindering the stability needed for life to evolve. The position and density of asteroid belts influence the chemical and physical development of planets. The snowline in a star system marks the distance at which water and other volatiles condense into solid ice. Inside the snowline, rocky planets dominate due to the high temperatures that prevent volatile compounds from freezing. Beyond the snowline, icy bodies and gas giants form, incorporating abundant water and other frozen materials. The location of the snowline plays a key role in determining the composition of planets and their potential for habitability. The age of a star system dictates its planetary characteristics. In young systems, high activity from young stars can strip atmospheres and bombard planets with intense radiation. Mature systems, with stars in their middle age, provide stable energy output, allowing planets to develop complex ecosystems. As stars evolve into red giants, their habitable zones move outward, potentially warming previously frozen planets. The age of a star system influences the opportunities and challenges for life to emerge and persist. A star's metallicity, the abundance of elements heavier than helium, affects the types of planets that form. high metallicity promotes the formation of rocky planets, increasing the likelihood of Earth-like worlds. Low metallicity favors gas giants and icy bodies, limiting the prevalence of habitable rocky planets. Stellar metallicity provides a snapshot of a star's formation environment and its potential to host planets like Earth. The activity of the central star or stars can significantly impact planetary atmospheres and surfaces. High-energy radiation from stellar flares can strip atmospheres or damage surface ecosystems, particularly around red dwarfs. Coronal mass ejections, powerful bursts of plasma, can alter a planet's magnetic field, leading to atmospheric erosion. Over millennia, changes in stellar output can drive climate shifts, influencing the habitability of planets. Understanding stellar activity is crucial for assessing the long-term stability of star systems. The diversity of star system architectures reveals how different configurations shape planetary outcomes. Compact systems like TRAPPIST-1 host multiple rocky planets in close orbits, creating unique gravitational interactions. Wide systems, with distant gas giants or secondary stars, may have more stable habitable zones but fewer planets overall. Chaotic systems with highly eccentric orbits or multiple stars often lack the stability needed for long-term habitability. These comparisons highlight the vast range of possibilities for planetary systems in the universe. The architecture of a star system shapes its potential to support life in profound ways. Systems with stable habitable zones, moderate stellar activity, and protective gas giants are the most promising candidates for life. Advanced telescopes such as the James Webb Space Telescope, JWST, and Plato are uncovering the intricacies of star system architectures, guiding the search for habitable planets. Understanding star system architecture is essential for identifying the most promising targets in the search for extraterrestrial life. Any chance of life in a star system has to be based on its design. The intricate web of forces that mold planets and their surroundings is shaped by a myriad of factors, including the gravitational pull of gas giants and the protective function of asteroid belts. One of the best ways to understand what made Earth conceivable is to look at the variety of star systems in the cosmos. We are getting closer to comprehending the cosmic circumstances that support life, with each new finding that contributes to the puzzle of habitability. As we explore the most habitable exoplanets, we're reminded of the vastness of the universe and the endless possibilities it holds. Thanks for watching. If you enjoyed this journey through the cosmos, make sure to like, subscribe, and hit the notification bell so you never miss an update. Share your thoughts in the comments below. What excites you most about the search for habitable worlds?